to start talking about how we were used to live in a technological disruptive world where the data proliferation and technology advancement were reshaping on a very yearly basis the entire competition at the global level, industrial competition at the global level. And a number of technology like Internet of Things, augmented reality, virtual reality, blockchain, 3D printing, robot, were some of the technology identified as disruptive technology, enabling a number of relevant megatrends in the entire geospatial industry. And in the last 2 years, when I'm saying 2019 and 2018, the leitmotif was that technology was, yes, indeed, accelerating the progress, but also causing an increasing uncertainty about the impact of this disruptive technology in our social life and also in our economical development. But as we all experienced it, entering in the 2020, we know that we experience a growing anxiety about existential threat as the slowing of the global economy, the geopolitical volatility, and last but not least, what we have experienced with the COVID. So we experienced it in that while in the last 2 years, so again, 2018 and 2019, most of the executive directors in the biggest industry were wondering about the impact of innovation in development technology in slowing the economy. Nowadays, we experience a completely different situation, and it's interesting to compare a number of surveys that have been conducted in the last years and see how nowadays a very large majority of executives, also in the geospatial industry, are wondering about the difficulties they are facing in implementing any innovation in this specific sector. So innovation is becoming again an important aspect that has to be integrated inside the specific business in each business process in a careful way, and it's important to keep our companies and innovative, so to be competitive at the global level. In this specific sector, the continuing innovation and the advances in computer vision, mobile computing, but especially in those portable display device, have brought a strong renewed interest in the domain of augmented reality and also virtual reality. And I think that the accessibility of the display technology now are bringing this technology much more relevant to be integrated in the business process, so to reduce the time to market in deploying product a solution. And within this workshop, we aim to discuss about the integration of geospatial technology and the innovation that we are experiencing, the technology innovation we are experiencing in the area of cross or extended reality, if you prefer, and how this kind of technology can be disruptive in transforming this attractive technology as something that can innovate the capability of our companies to be competitive at the global level. In this context, we have shaped an agenda, and this agenda foresees 6 presentations. The first one will be provided by William Bernstein from NIST, and Bill will introduce to us how the adoption of extended reality technology in manufacturing environment is continuously growing, and he will present a number of activity that he has conducted within a number of projects, demonstrating how geospatial standard might be functional for the deployment of the augmented reality technology in the context of smart manufacturing. I will perform a second presentation where I will focus more on the role of spatial data infrastructure in the implementation of the fourth industrial revolution agenda. And the third presentation will be provided by Josh Lieberman from OpenGIS Consortium, and he will introduce us the GeoPulse standard, who are real or virtual objects to be positioned, including in the space, including their orientation. The fourth presentation will be provided by Radowski Raphael, who will present how augmented reality rely on accurate maps and the importance of tracking and effective tracking for deploying efficient augmented reality application. And the fifth presentation will be conducted by Johannes Scholz from Austria, and TU Graz from Austria, and he will elaborate his presentation, providing a very interesting example conducted in the context of semi-manufacturing industry. The last but not least, we will have Bruno Simoes from Vicontech Spain, who will present the idea of digital twin, and his presentation will highlight some future research direction aiming to integrate ghost reality technique with the support of geospatial technology. So this was my short introduction to the workshop. I would like to thank you once again to be here with us, and I will leave the floor to my colleague, William Bernstein, who will start with this presentation. Thank you, Bill.
So thank you, Raphael. So on the right of the room, we have the presentation already loaded. Oh no, it's not there anymore. So can you please stop sharing, Raphael, and I'll just load up my screen on the main screen. Raphael. Oh, wait, maybe I can already. Okay, there we go. Apologies about that. So I'm really excited to share with you some work from NIST. Just to give you a little bit of background, I am a mechanical engineer. My expertise is really in CAD/CAM, or computer-aided design, computer-aided manufacturing. I have some experience with visual analytics and data visualization, and have been dabbling in augmented reality for about 2 years now. And since I started, I reached out to Johannes Scholz, who's here, and also Raphael Diamicis, who also is the co-organizer of the workshop, to get two very important perspectives, one of which Johannes is representing, I would say, kind of the GIS community, or the Geospatial Information Systems community, or research community, and Raphael is representing more of the mixed reality, something that's a little bit more traditional to the ISMAR folks. And I really think these two areas are extremely vital for realizing the full potential of Industry 4.0 and smart manufacturing. And I hope that this presentation will give you a glimpse of the kinds of problems that we're dealing with even outside of XR technologies, just basically harmonizing different standards within Industry 4.0, or we call it smart manufacturing at NIST, to give you a sense of how these AR and extended reality technologies can assist in these mapping areas, or these alignment areas. So before I start, I wanted to give a brief background of who I am and what positions I hold right now. I lead a project at NIST called the Extended Digital Thread Project, which is focused on what I just mentioned, really the alignment and registration and mapping of different smart manufacturing standard representations across one another, with or without XR. And I'll get into some examples of what that means. I also chair the newly public NIST XR community of interest. And if you're interested in this, I feel free to Google XRCOI, NIST XRCOI should come up, your first result. What this represents is a group of NISTers, other researchers at NIST, that are, I would say, utilizing XR technologies to solve scientific problems. Some of them are more focused on the underlying tools themselves. For instance, we have people that are highly engaged with the Kronos group and other kind of AR, VR specific communities. But most of us are just kind of using XR to solve a problem. So we have a small webpage that you can check out. And if you have any questions or interest in that, please do let me know. I also co-chair a military-focused group called the Digital Information Visualization Working Group out of Mantech. And what this group focuses on, as you can tell by the title, it's much more broad in its encapsulation. But because of AR and VR and immersive visualizations basically eating up all the interests of the folks that are involved, the last year has been basically entirely dedicated to things like asset tracking, AR delivery systems, and presentation systems. So it's, to me, undeniable the importance of this area to bring Industry 4.0 into realization. So before I begin, because I work for the U.S. government, I'm going to share some opinions and commentary. These do not represent any kind of formal approval or endorsement by NIST. Of my colleagues here, I give a brief background of smart manufacturing and Industry 4.0. I'd then like to dive into and discuss what the standards are in the I4O areas, which might not be as well represented at ISMAR, but in many other conferences they are. Then I will finish my talk by explaining what I call the gap or the moat between the standards that are taking place, the standards activities taking place in the I4O community, which is kind of like the bread and butter of what we do at NIST, and the mixed reality community, which you'll hear surely more from Josh Lieberman about what's going on at OGC. I'll just describe some relevant standards for our work with respect to what we're doing at NIST, and a quick sampling of some of that work that we've been able to achieve. So first, for those that don't know what National Institute of Standards and Technology is, we're located in 2 campuses across Gaithersburg, Maryland, which is a suburb of Washington, D.C., and in Boulder, Colorado. Some of our most worthy work, or some of the most famous work we have, is related to the atomic clock, which is essential for the enabling technologies of mobile computing, because it enables the GPS across your smartphone. I think there's 5 Nobel laureates, or I'm sorry, Nobel prizes associated with the work on atomic cooling that enables the atomic clock. And there's many other things very useful for this community. For instance, we generate a lot of data. For instance, we have a net zero house that's representative of common, or I guess, and it's in quotes because my house isn't that big, but the average American household, to show how you can generate electricity through renewable technologies. What's more important for this community, I think, is there's a very substantial cybersecurity framework, which is used all over the world for categorizing threats to different IT technologies. If you haven't heard of that, I would really recommend checking that out. And also relevant, particularly for I4O and smart manufacturing, we have retrofitted our existing machine shop on campus that streams live data 24/7. Well, I shouldn't say 24/7, as long as the machines are running on the web for people to use. And that's been used by a wide variety of industries across the world. So the way that we define smart manufacturing at NIST, it's actually considered a focus area across the entire campus, is the synthesis of advanced manufacturing capabilities with advanced digital technologies. And I've just placed some of those examples here, things like additive manufacturing, the whole idea of model-based engineering or model-based design, distributed supply chains, which we're getting a big taste of those effects in COVID, coupled with these just quick examples of digital technology, things like AR, cloud computing, IoT, you can name many more. And what our role at NIST is to engage with the standards making community and provide the measurement science to allow industry to more easily obtain value from these different perspectives. And I've just given a sampling of some things that you might consider smart manufacturing or Industry 4.0. So I want to be very clear that I'm using those two terms interchangeably as synonyms, and there's really no more to that. Some of the things that we would consider smart manufacturing ideas are cloud computing for manufacturing, mobile computing for manufacturing, security, traceability, and so on and so forth. And what you'll hear from Bruno, which I'm very excited to hear his talk, will be more about this concept of digital twin, which is extremely important if you want to achieve that. You need to have a clear-cut virtualization of the physical space or of the manufacturing floor, which I think is a really key concept of this workshop. So just to give you a sense of the kind of data we're dealing with. So if you go through a normal kind of engineering workflow from when you're designing a product, as you see in the top right here, hopefully you can see you can't see my mouse, it's okay. In the top right, the box that says A1 design product, and you feed forward into eventually when you're actually manufacturing the product, and then it goes into the consumer's hands, and then it's eventually either recycled, reused, or eventually disposed. There's lots of information that's passing through these different stages. The thick arrows represent forward feeding or informing information, while you have many different kinds of back-propagated data flows or information that could influence those stages. But to get a sense of those dotted lines that you see there needs to be standards that basically report data in a consistent manner so that those upstream processes can better behave or react to that data. And that kind of gives you a sense of why standards are so important. If you tried to do this in an ad hoc manner, this would be a mess, almost as probably even messier than this figure. But it's quite important, and especially when we think about the ideas of resource consumption and energy efficiency, to realize those savings in terms of energy or material, all those information feedback loops are extremely important. So my point in showing you that is a lot of the standards that we work on, the smart manufacturing standards, are really aimed to provide that feedback loop. So to give you a sense of some samplings, and there's more information on the next slide that I'll share, some of the most current or appropriate standards that we deal with here is things like ISO 10303 or AP 242, which is basically a standard that captures design information. So if an engineer designs a product and they want to feed it into a manufacturing facility, it captures not only all the geometric, idealisms of the product, but also information about what are the requirements of that design, what are the tolerances, how close to the ideal part do we need to manufacture it to realize its potential. And then in fabrication, there are two kinds of data that are captured there. There's the planning data, meaning the process plans, what kind of data needs to be fed into these machines to produce the part that's described by design, and also how the machine actually behaves. And those are drastically different things. And I'll share some research and showing how we can relate those two together. And then finally, once the product comes off the line, we need to get a sense of how well we did in fabrication, and we do that through inspection. There's some standards there as well. And here's just an example of how this kind of communication can help. So in the bottom right, what you see is a part that we built on our test bed. And what you see in the graphs is basically in the bottom graph, we have a simulated view of how long we thought that build to take. And on the top, you see how long it actually took that we gathered from our test bed. And as you can see, they're drastically different. I think they're even twice as long as what we expected. And you can see that there's certain features that caused it to be longer. You see the highlighted in red are those sharp angled features on those fins. And the reason why it took longer is because the operator needed to slow down the machine unexpectedly to make sure that they would achieve the tolerances that's set forth by the design information. So these kinds of feedback loops would not be captured unless we were properly and consistently capturing that information. So what's the connection between what we can call this as the digital thread and other trends? So there was a recent report that came out of Industry Week that showed the hottest trends maybe in the next decade. And what's clear is that wearables, the use of AR, and kind of ubiquitous 3D scanning is everywhere right now in manufacturing, and it will continue to grow. Okay, so I hope that kind of set up the stage for this digital thread perspective or the manufacturing standards and the AR standards. So now I'll share a little bit of work related to more of the digital thread work. So as I already mentioned, there's lots of standards activities in Industry 4.0, smart manufacturing systems. If you're engaged in any of these, you'll know that even one of these organizations would have many, many different efforts that don't necessarily align well with one another. So the real problem here is harmonizing these standards at scale. And I can't see Josh's face right now, Josh Lieberman, but I'm sure he's smiling when he sees this, because this is even a challenge with, like I said, within one of these organizations. Some of the Industry 4.0 standards that maybe you should check out or you can check out, and I said plus in parentheses because some of these aren't necessarily just smart manufacturing standards. For instance, like SysML, the new version 2.0, which I think will come out maybe next year, is certainly a very high-level framework that can be used across many different kinds of domains, but it's heavily used in manufacturing. I already mentioned MTConnect, which is a way of capturing data coming off machines. It's a protocol for reading machine controllers. I mentioned the huge step series, which is very large. There's a lot to it. And I've mentioned some other messaging standards there, as well as PMML and PFA, which are an interesting way of capturing machine learning models. The big takeaway of all this stuff is that data representations really matter. And the choice of how you represent this data is dependent on the domain and what problem you want to solve. So harmonizing across these different standards efforts is no easy task because they weren't really designed to do so. I mean, maybe there were some that were, but mostly they are they're designed to accomplish goals set forth by those specific channels. So if we revisit the scope of what we're doing in digital thread, we have these three kind of buckets of design, fabrication, and inspection. What we've done in our lab is we've kind of grabbed all different standards from these communities to test out how we can harmonize them together. Now I'm just going to give you a quick example of some successes that we had in doing this. It has nothing to do yet with AR. It just shows the kind of effort required to harmonize across standards. So in one project, what we tried doing was using an OWL representation or knowledge graph to harmonize data coming from design as step AP242 and data coming from the quality information framework, which is a pretty substantial inspection representation. And we had this pretty simple three-part assembly, and all that data is available on the web. And this just gives you a quick example of the difference in the way in which the data is represented. On the left, you see kind of a graphical representation of STEP, which is modeled in Express, which is kind of like a, I guess you can consider it like an object-oriented language. And then QIF is represented as XML or in an XSD format. And basically, we develop tools that are available online. Feel free to check them out. I have links at the end of this presentation. They're also at the top right of the screen, where we transition XSD to OWL, and then we also transition STEP to OWL. And in fact, I think for this group, it would be interesting to hear that this Onto STEP work can also work across IFC models, and IFC are also modeled in Express. So we were able to reason then by finding the commonality across these different knowledge graphs. But some of the data, we can't do that. It's not in a form that you can simply just throw it into a knowledge graph and churn. One example of that is back relating the execution data coming off a machine with its plan. And let me give you just a quick example. I know this isn't the perfect group to talk about this about, but I think it's worthy of explaining because we did some interesting spatial registration between these two different coordinate systems, which we've used that as an analogy in our AR work. So the idea here is that this one code that I've highlighted on the left produces a certain block of execution data on the machine. So the question is, if you don't have this clear relation as the controller is writing the data, how do you then back relate the execution data back to the planning data? So what we did is we developed an algorithm that basically uses different kinds of clustering techniques along with dynamic time warping to then basically encode a certain execution block with its predecessor process plan. And yeah, I'd be happy to share the latest progress with that video. So I just realized I'm taking up a lot of time. So I'm going to move on to what the main point, my main message I wanted to get to was this idea of we have all this work going on in smart manufacturing in terms of harmonizing standards. What happens when we bring mixed reality in? And the first thing we did was we just looked at what's going on in the mixed reality space. And very similar to smart manufacturing standards activities, there are many players in this space. There's a lot of good work coming out. They're all focused on very different things. And they are also approaching a similar problem where harmonizing these standards together becomes very, very challenging. Okay, so again, the main challenge here is not only harmonizing within XR, it's harmonizing the XR standards with the smart manufacturing standards at scale. And let me give you a broad perspective that I think might engage the group in some discussion. So the way that I think about XR is that, and especially the standards community, is that there's really two main kind of roles for standards. One, on the left screen, you see how we're going to capture the world and how we're going to represent that world in a computer readable way. And on the right, what you see is how we're going to basically present that data to users through different modalities. Okay, and there's a wide variety of different standards. I'll just give my own two cents. I'm a big proponent of OpenXR and WebXR. I think they've done great things. WebXR is in W3C, really substantial API there, a lot to play around with. OpenXR is an effort by the Cronus Group, really focusing on this interoperability challenge. But what we want to do, okay, and I think hopefully this resonates with people watching, is that, whenever you need to make a industrial XR pipeline, what you have to do is link these two different XR perspectives to domain-specific models. And those can describe devices, people, spaces, plans, materials. Basically, what that blue box is our SMS standards, our smart manufacturing standards. And our idea of our lab at NIST is basically to automate the piping between those domain-specific models with those two XR perspectives. Because right now, that's a lot of manual labor, and they require really interdisciplinary teams, people that understand the manufacturing space, or I should say that have experience there, and know how difficult, how dirty the data is. And then those, obviously, the developers, the people that actually make this stuff look presentable and make it work in environments that are changing. So here's some examples of the kind of stuff we're playing around with. So one quick, this is obviously not groundbreaking, but I mean, it just shows the power of which standards can play in this space. So we borrowed the good work from the OGC folks using IndoorGML and basically connected it with our smart manufacturing lab that has a bunch of machines that are beaming up MTConnect data. And after we had this geospatial representation of the shops, we can basically find real-time information about those machines and just give the operators, or I guess the foremen or the managers of that the machine shop, a quick idea of which machines are on. The machines that are on and working are in red there. which are available. There's just one down there in green, and then which are offline. Maybe there's something wrong. Maybe the data is not streaming, and those are in yellow. Okay, so we were able to achieve that. Right now, we're working on a WebXR version of this so that people can jump right in on the browser. Another thing we are interested in is, we have this small space, a small lab, is, how do these geospatial definitions help with tracking and registration? So we've just developed it's a rather simple IndoorGML model of our lab, and we've been playing around in that space. So, and what we've done is we've placed some digital objects around the space. We're working on different ways of registering those objects, and we've aligned, or we've kind of mapped those digital objects to real data coming off the testbed. So what you see on the right is just controller data from the testbed. Obviously, this isn't the actual testbed, but it gives us an idea of playing around on how we're going to visualize that data. Another interesting idea is the use of the layered feature in IndoorGML to achieve something that I've seen way more complex than I think it needs to be. So the problem here is, let's say you have a spinning saw in a very dangerous manufacturing environment. I know I've seen people use various computer vision techniques to consistently identify where that spinning saw is and make sure that there's no digital objects occluding it. So in the case that what we've done is we've basically just modeled in a layer in our IndoorGML model and then change the rendering within Unity. I mean, this is very, very simple. It's just an idea to show some things you can get for free if you have your space already modeled in something like IndoorGML. We've also looked at how these standards can support multi-camera, multi-XR framework support. So in this case, I don't have time to really get into the details, so maybe I just skip to the video. We have two cameras that are represented across one another in this networking framework using drastically different tracking frameworks, different cameras, and the idea is that they can send messages across this geospatial definition. So we're kind of experimenting with that. Some other work that we're very much interested in, actually there's a tutorial right now going on. I'm not sure where it is in our virtual world, but there's a tutorial right now about the video on the left of the screen you see there by Raphael Radkowski's team. We partnered together, and he's developed an open source tracking tool where you can trace, we can track an object like a cart as that gentleman's pushing around. What we would like to do is test the capabilities of the different asset tracking technologies. There's many out there, but there's really no formal baselining about what these different technologies can achieve and what the end users can expect of how well they can get the job done. We also are very interested in testing the updatability and robustness of our multi-camera scenes. What I mean by that is I shared this very brief video of us messing around the lab across IndoorGML and sending messages. So our question is, once you have an AR installation already embedded in one of these physical spaces, what happens when you add an additional camera or an additional device or additional headset? We want to make sure that somebody can get online within minutes rather than hours. And we actually want to test how capable these different standards are in helping us do that. I mentioned some of these works and ideas. Actually, I'm sorry, this is not supposed, it's the wrong title, I'm sorry. This should just be more standards that we're very much interested in, that we've been tracking and using in our work. And I wanted to put this here for others to on their own to go check them out, what they're up to. We'll hear from Josh Lieberman about GeoPose from the Open Geospatial Consortium. I mentioned the real great work of WebXR from W3C. There's an interesting standard. I don't think it's as well known as the WebXR standard, but there's a standard out of Etsy that basically standardizes the terminology across these different perspectives in XR. I think that's very helpful and very useful. I think a lot of us are speaking different languages. We can't even agree on what XR stands for example. And Sensor Things API is a very interesting standard, which is basically a geotagging IoT standard, and we're very much interested in using that. We recently just attended, and I hope this is kosher to say. Maybe Josh will say it's okay, but we went to a IndoorGML 2.0 meeting, and what we really liked about this meeting is that many of their proposed improvements to IndoorGML are really going to address a lot of the issues that we experienced with it, that I wasn't able to really dive deeply into the problems that we had. I think one of the core problems that we had was actually the one that you see in the top right, this idea of supporting objects and features within a room themselves. So for example, IndoorGML relies on some external standards to provide support for digital objects like 3D or digital assets like machines you would see in a manufacturing shop. So now it seems like they're going to support it. And just some summary of some on-looking ideas that we have that maybe people have some additional questions. For instance, we're interested in using Sensor Things API or some other IoT technologies to really test out the appropriateness of how we can geotag different moving assets, like whether they be carts, they can be small micrometers, other tools that get traded between machines. We actually started our conversation between our co-organizers with a simple question of where's my tool, right? And that's actually a quite difficult problem to solve in an automated way. We're also interested in integrating what I shared at the beginning of the presentation, this idea of how you enable the digital thread through mapping these different standards and try to realize some value within an AR environment. We're working towards that. And then also something that I didn't talk about at all yet is I think there's a massive problem in reliable and exemplar 3D content management. So right now, a lot of what people are using, it seemingly in research studies, are either exemplar kind of digital assets, but not they don't pose like the realistic challenges that people face in transitioning, for instance, CAD data to an XR experience. An example would be there's too many triangles, there's too much kinematics information, there's a loss in behavior of the models as opposed to how rich the fidelity of the design model was. All these are big issues. Also, the way in which those design models are curated might be extremely different. So what we've done is we've basically rehosted an old, it's fairly old, from the 90s, an engineering design model repository, which was originally the work of a postdoc who now is a named professor at UMD, University of Maryland. And the idea here is there's a wide variety of real company engineering models, and we'd like to test their capability within some kind of virtual space. And we would think that they would be wildly different. So it poses some interesting challenges for us to test. Here's just a dump of the publications that I've been pulling information from for this presentation. There's also some links to open tools that we have available for folks. For instance, this step to OWL, which we call onto step at NIST. Like, again, it doesn't only work with step, it also works with any express model. Like, for instance, if you want to convert an IFC, which is used in the construction community or infrastructure community, to an OWL representation, it should work. If it doesn't, please let me know. And we also have some other simpler tools like a step to X3D translator that's built off of an open toolkit called Open Cascade. And like I mentioned before, we are very proud to fork this open tracking toolkit, which is being presented as a tutorial right now called Tracking Expert Plus. So I hope that came clear. So if anybody has any questions, I'd be happy to answer. Thank you.
Thank you very much, Bill. And I can just echo the solicitation of that Bill has made. If there is any question, you are very welcome to ask it for now, or at the end of the workshop, we can also save some time to eventually collect some, not only questions, but also some interesting reasoning on findings can derive from the set of the presentation. So thank you very much, Bill. If there is any question, I'm sure that Bill will be very happy to reply to you. If not, yeah, thank you. I will now try to share my screen, and hopefully everything will work as expected. Okay. So I assume that you see the screen and everything is fine. So I will continue with my presentation. That as recalling what Bill has said, I will try to provide a perspective that I developed since my interest, since I have been starting the domain of immersive technology, but I also benefit a lot from the wave generated by the digital Earth paradigm. And I will try to focus my presentation on a specific system architectural aspect, highlighting the importance of spatial data infrastructure in the context of Industry 4.0. And the next slide, this one, describe in a very visual manner the interest and the historical context that characterized my research in the context of digital Earth combined with immersive technology. I was extremely fascinated by the concept of digital Earth that, as you know very well, has been coined by Al Gore in his great book, Earth in the Balance in 1992, and that eventually was developed in the very famous opening talk at the Computer Science Center in 1998. And at that time, I was enjoying my PhD research at the Fraunhofer Institute for Computer Science in Darmstadt, working with one of my very first conference I applied, and I remember that one of the paper was envisioning the paradigm of mixed reality. And it's right, it's fully right, Bill, when he's talking about the difficulties also in harmonizing the several terminology we use. He was referring to the XR acronyms that is both used to describe extended reality or cross reality, and both of them, they have two completely semantic different meaning. When we refer to cross reality, we foresee also the possibility to use a sensor actuator transforming the digital content we might experience either in a virtual or an augmented context. While the extended reality is the terminology used to describe the entire portfolio or possibility that has been usually mentioned that goes by augmented reality, augmented virtuality, and then full virtual reality. But I don't want to recall those aspects, then just that it was impressive as at that time Al Gore was capable to describe the digital Earth paradigm as a multi-resolutional and three-dimensional visual representation of the Earth. And this paradigm was capable to exploit the advantage of the georeferenced information that were already at that time collected and available through digital library. This was the terminology that we used. And this new paradigm has generated a profound change in the geotechnology context, reviewing the use of GIS information, geographical information system in a plethora of application domain, archaeological, urban planning, geology, and in my opinion, last but not least, also the Industry 4.0. And indeed, my presentation will try to understand how this paradigm might fit or not, and what are the current gaps. This video describes very well my passion, and also why I was stimulated to work and to move from the use of virtual reality or augmented reality in a typical and classical industrial manufacturing context, where this technology, magnetic technology, were used for assembly, disassembly activity, or for ergonomic analysis, and so on. And I was so excited about the possibility and the data collected by different technologies, satellite, drone, and that they were capable to generate such enriched and realistic environment that were eventually, over the years, not only magnetic because of the realism they propose, but also because they were enriched by semantic information. And in this context, I think that the geographical community, the geo community, definitely the OpenGIS Consortium have played a pivotal role in transforming this information useful to support the decision-making process in a number of application domains. And the last part of the video, so the representation of an urban environment that has been empowered by one of the, in my opinion, one of the most powerful standard, CityGML. And it's surprising if you look at the system architecture that characterizes interactive geographical environment, then I will say something on this regard in the next slide, is similar to the one that is described by the Industry 4.0 framework. On the other way around, these two ecosystem seems to be completely detached. And it's just apparently, as I will try to demonstrate within this presentation, but you can try to conduct bibliographic research, and you will find out that certain keywords like spatial data infrastructure and Industry 4.0 produce almost no result at all. And similar things can be also experienced if you will perform your bibliographic research, coupling terminology like, again, Industry 4.0 and geographical information system. In this case, you will find probably some research work, but most of them are related to the construction and civil engineering domain, precision farming, forestry sector, but on very few, I would say almost no publication highlighting the two domain, the manufacturing one and the geographical information system. And despite there is a lack of vertical research activity demonstrating the needs to fruitful synergies, the industrial domain is working in a completely different direction. Those that are familiar with virtual globe, they know for sure the current cooperation going on between platform like Cesium.js and famous automotive company as well. So there is some correlation between the framework that characterizes the Industry 4.0 and the one that characterizes the paradigm of digital earth. And actually, these two frameworks, none of the two, in my opinion, yet has fully exploited the synergies that can be implemented by those two very interesting ecosystems. Just I would like to spend a few words about what is a spatial data infrastructure, just to also keep this presentation at the informative level and probably to pave the way for further research activity that might foresee also the involvement of standard organization. We have two very important, two representatives of two very relevant standard organizations in this workshop. And the spatial data infrastructure, most of you already know, is an infrastructure that is designed to facilitate the access and the management of digital spatial information. And a geoportal is just a gateway, a web gateway site that allows the user to search, discover, access, and view geospatial resources that are stored within a spatial data infrastructure. So a spatial data infrastructure evidently play an extremely important role to exploit the power of those geospatial resources. And although geographical information systems are extremely powerful tool for the treatment of geographical information and also for the decision-making process that is consequential to the collection of those data, the rise of virtual globe have demonstrated how this technology can become immersive, pervasive, and nowadays, since almost years, this virtual globe paradigm has been implemented also using immersive technology, both augmented reality and virtual reality technology. But this infrastructure has been not yet fully implemented in the paradigm of Industry 4.0 that is still attached to certain system architecture paradigm that are still a classical one. This very simple picture describes how spatial data infrastructure, by means exploiting specific web services, and a number of them are listed in this slide. So coverage services, feature services, processing services can facilitate and implement this interactive interaction with this interesting and powerful infrastructure. And all those could happen in such powerful and impactful way because the deployment of these web services as a standard. And as I said, OpenGIS Consortium has played a very important role in this regard. And in the last years, I experienced also with a number of projects. I was very lucky to start to implement the importance of spatial data infrastructure in the in immersive system architecture, in transforming the beauty and the power of those data in something that would be functional for the decision-making process by means the implementation of an analysis and synthesis paradigm. And starting since 2002, 2003, I have been involved in a significant number of projects funded by European Commission, but also other agencies in this industry, last but not least, the NATO organization, exploiting this data in the context of immersive technology. And interesting aspect that have characterized this, the use of this framework, the use of this infrastructure, was the possibility to integrate different information services, and web processing services have been functional for this, the orchestration of different services capable eventually to implement application domain needs that would have foreseen the user being involved in a simulation process, but also the possibility to generalize information, to create information, and eventually to interact with this information. And this, which is a very simplified version of a more powerful digital Earth system architecture, capable not only to ingest, digest, visualize, retrieve data, but also by means of specific added value services, also to be functional for specific application domain. And in this picture, I just simplified a number of application domain that I have been involved with, leading as a principal investigator a number of European projects, as I mentioned to you before. So in this context, we have a number of interesting components of the spatial data infrastructure that, as I said, is the technology, the policy, and the standard, but also the human resource necessary to acquire, process, store, and distribute those information. I mentioned to you also the pivotal role that can be played by, that is played by a geoportal that can become the application layer, the presentation layer, if you want, of how those information are eventually represented in a more interactive manner. But also, what is extremely important, the role played by the metadata, the standards, and the web services that implement this system architecture. And the combination of this vision with the possibility provided by immersive technology was immediate for me. And the first project I started to combine was called titled the Sketch AR. It was, if I'm not wrong, funded by the European Commission in around the year 2000, 2001, and we were capable to ingest and distribute geographical information through different immersive device using different technologies, so titled display or interactive screen, and also the very heavy and bulky helmet-mounted display that we were capable to use at that moment, but exploiting, as I said, the power, the potentiality, and the powerful of the immersive system architecture. And at that time, still I'm convinced about this, the metaphor that is used as example, I would like to use the one typical of an augmented reality, where the human perception is enriched by the computer perception, correct? Is very similar to the one that we have drafted in describing the atypical geospatial system architecture. So we have the sensors that are collecting the data, and we saw also in the initial video how many sensors we have also in the geospatial domain. There are also standards it's available to manage those sensors, to orchestrate how those sensors are collected. Then we have this interesting software component that we often like to call in the context of augmented reality as a context analyzer, who is capable to combine, blend, integrate the information that are captured by the sensor with the information that are embedded in a scene graph. And then we have what I call it the augmented reality presentation layer that can be similar to play a similar role to a geoportal. And indeed, we had also investing research activity aiming to echo this paradigm, the augmented reality paradigm associated with the geoportal. So I would like to be a little bit quicker because I would like to give to my friends also the possibility to express themselves in a very comprehensive way. But what was, in my opinion, a very disruptive standard that has transformed the use of those geographical information has been in the civil urban planning domain and many others, the CityGML, capable to contain very complex data sets and to represent them, so an urban environment, and to represent this urban environment in a geometrical, in a semantic, and also in appearance way. In my opinion, this has been one of the most powerful standards that has changed also, again, the use of spatial data infrastructure that has been empowered by virtual cloud. And I would like to recollect now, going to conclude to my presentation, aiming to conclude my presentation with something that I miss, in my opinion, as a standard powerful enough to face the challenge proposed by Industry 4.0. Most of my colleagues, as I am, are using IndoorGML as a powerful standard, indeed it is, to represent industrial assets. But, and then this is my proactive and provocative finding, probably we have to focus our attention also in a specific standard capable to describe the industrial scenario in a more transversal way, because an industrial scenario can take place both outside or both indoor or in outdoor environment. So I think that this is probably one of the aspects that is still require effort from the standard community, and this would be probably very beneficial in trying to couple the potentiality of the geospatial industry with the one of the industrial framework that I presented since the very beginning. And again, I would like to, in a positive way, provoke you to see how much research has been done in analyzing the potentiality of those two ecosystems, but you will be probably either capable to help me finding a proper research, or you will find that a lot still has to be done in this dimension. And I would like to conclude my presentation giving you also an economical perspective, how those two framework ecosystem are extremely interconnected. So this is a picture that I derived from geospatial media and communication research that has been presented in 2017, and you will see in this picture the technological trends that are influencing the geospatial industry. And those trends are the same one. I don't need to go through all my slides, because you remember very well the one I described when presenting the Industry 4.0 framework. So cloud, Internet of Things, automation, robotics, big data. Another interesting picture is derived from also this report that produced that explain the key technological driver. And you see the technology we are that we love, and that's the reason why we are here, which is augmented reality and virtual reality. And you will see how position system, but also 3D scanning technology, as Bill was mentioning before, are fundamental in the implementation of the augmented reality paradigm, for instance. This was clear from the Bill description of his research activity. So another evident correlation between the two one. Probably this one is the picture and the slide that even more than the research, the bibliographic research, demonstrate that still there is a lot that has to be done in the manufacturing domain to exploit the geospatial technology. And if you see at the right side of the picture, you will see the impact of geospatial technology in terms of dollars in the manufacturing context is not at all comparable to the one that we have in the first part of the list: transportation, utility, and construction. And last, also extremely important element that will also facilitate the presentation of Rafael, my colleague, who will talk about tracking and how important it is to tracking and monitoring the presence of the object. You see in this table the I call it augmented global network system already existing, and a performance that this technology, key technology in the geospatial industries, are functional for a proper deployment of augmented reality. And last picture is the one that describes indoor location services, and motivated also my initial recall to work on a standard that describes the geographical asset characterizing the industry 4.0 paradigm. You will see that very in this picture. Manufacturing is not present at all. It was present in the data that I had, but it was so visible that was not capable to be reproduced in the graph. So this concludes my very quick talk, because I believe that it's very important also that at the end of the day we are capable also to collect some finding, because we all came from a different specific domain, and a transversal vision will for sure facilitate the understanding how those framework. So the one characterizing industry 4.0 and the entire geospatial industry are functional for the innovation that, as I said since the beginning, are a key aspect to keep our industry competitive at the global level. So thank you very much for your attention, and I would like to leave the floor, switching to the next colleague that will be in this presentation. So the first thing I have to do is to stop to share my screen, and I'm so glad to introduce Joshua Lieberman from the Open Geospatial Consortium institution that has characterized also my growing in terms of competence and interest in the last 2 decades in this very exciting domain that has also characterized my research career. So, Joshua, I hope you are ready to start, and I think you should be able to share your screen, correct?
I will give it a try. Thank you, Rafael.
Thank you, Joshua.
Okay, share my desktop. Yes, there we go. Well, that seems to work. Let's see what happens when there. You see my slide?
Yes, perfectly.
Excellent. Okay, so I want to first thank you, Bill and Rafael, for setting the table here. And so what I'll do in a few minutes is to load a few more appetizers on your plates, and hopefully that will lead to good and interesting explorations of taste and not indigestion. But particularly, I want to look at the XR and the use of XR and the representations in the indoor and manufacturing environment from the point of view of geographers. What have we learned that we hope will be valuable in some of these other domains, which are not, I will say, not traditionally mapped domains, although at one point, just as a story, I was working with people in consumer packaged goods, and it's very important in that community where products are placed on shelves in a grocery store. And they had drawn these diagrams of where on a particular set of shelves particular products were arrayed. And I said, "Oh, you're drawing maps of the placements." And they said, "No, we're not." So thinking of that as a map can be difficult, but in fact, this skill and the way that technology is upgrading it is very common. So first of all, I'm Josh Lieberman. I'm Director of OGC Innovation Program. So the Open Geospatial Consortium is a standards development organization, but it does a few other things to support that. Our main mission is to make geospatial or spatial information easier and more valuable to share, findable, accessible, interoperable, and reusable. And our standards and other work are directed to fulfilling that mission. So I want to talk a bit about it. What is OGC? And then what is it about geospatial information science and digital geography that really are applicable here and that leads to addressing certain challenges with 3D objects and real-time reality that can be, we hope, solved through an emerging standard called GeoPose. So I'll talk about what GeoPose is, how it's defined, and then how it relates to other standards that are being used for XR and for similar applications. So first of all, OGC is a global consortium, and it represents over 500 industry, government, research, and academic member organizations, including NIST and others. And it's really a hub for thought on spatial data, spatial information, and innovation. And it's an open standards organization, but it supports a whole range of activities around developing standards, testing, innovating, conforming, communicating, and many others. So it's interesting that this interest is about equally divided between commercial, government, and are valuable in creating markets and leveling playing fields and helping people to work together by sharing knowledge and having a common basis for that knowledge in all sorts of different communities. One thing I will mention, what is a standard? I don't know if anybody has said that, and I actually got, I think, the best answer to that from some of Bill's colleagues at NIST, which said a standard is an agreement. And in everything we do, and particularly in technology, where different pieces have to work together, we have agreements on how those work together. We make those when we need them, but we soon in many fields discover this is a lot of work. We have to keep negotiating and using diplomacy and coming up with agreements so things can work together. And a lot of times the old agreement and the new agreement look a lot similar. So a standard is really just a a good agreement, which is really reliable and reusable, and something that people can make use of instead of negotiating new agreements for things to work together. So that's what we take as the standards. So different programs. So you see in the lower right-hand corner, we have the standards program. We develop standards, specifications that are these reusable, durable agreements that are understandable to at least the information community that developed them, and if we do it well, across other communities as well. In order to have trust in implementations of those standards, there's also a compliance program that tests implementations for doing this. But there's these two other pieces. You know, if we create these standards and nobody knows about them, or if people have needs for standards and nobody tells us, then not going to work either. So communications and outreach is a very important part of this work. And mostly these agreements to support distributed communication and synergy among technologies is difficult to test because if you didn't have the standard, you couldn't do the things that it enables. So we have something called the innovation program, and I call that the what if program. So instead of saying, we came up with a standard, what can we do with it? We say, well, what if there were a standard? What could we do that we couldn't do before we had that standard? Let's draft up something, rough consensus and running code, and see what we can do. So a lot of what I'll tell you is standards or evolving or emerging standards that have come out of many innovation program activities, including with partners such as NIST and others that have supported this work. So why do we need standards? Well, because we all need to work together. And when we don't have an agreement, or when we have different understandings of those agreements, then bad things happen. And particularly when we don't have spatial standards, or we don't understand what we're communicating with our spatial standards, then bad things still happen. And the consequence of, for example, being a little off in your spatial datum or units and thinking that you were not, well, here's a good example. So how do we do that in terms of space? So we have what I call the dual model for space, which is that we model everything, right? Because we want to simulate or predict or verify. In the case of space, we don't have a direct digital representation of space. We have, you know, a number for temperature, for example, but we don't have a number for this room. What we do have are geometric models that enable us to translate space into numbers that can be understood by machines and also by us, in fact. And there are many manifestations of that. So one manifestation is a map. So we put pictures on paper that are the model for the reality that we're trying to communicate. We have more precise quantitative representations, and there is this alternate perspective that we always work with. One is that we assume that reality has a value of something at every point. So look at the scene of the city, and there is a color or reflectance or a travel time for a LiDAR pulse for every point in that scene. So that gives us a lot of information, but not a lot of meaning. It just says, here's a lot of numbers. And so there's a process that we all explicitly or implicitly go through of saying, but we recognize, we discern, and we can reference in discourse and conversation specific elements of our reality. And that's the term feature that we use. We took talk about vectors, we talk about features, we talk about objects, we talk about semantics, the thought applied to reality that gives us these pieces. So we have then a way of recreating that reality, for example, on a map. And one of the ways that I try to put XR into perspective is to say that it is not new. So we talk about we don't agree on X. So what do you do when you use a map? What do you do when someone describes directions to you? What you're doing is applying that additional information to the reality that you can see, if you can see where you're going, or it can be the reality that you imagine when you have a mental picture of the terrain that you need to navigate around. So I refer to that as imaginative reality. Sometimes it's called map skills. So people can do that. And what technology is now enabling us to do is to do that imagination more quickly, more accurately, more easily with the augmented or virtual immersive reality than with pretty difficult to obtain and sometimes especially difficult for some people map skills. So in order to do that, though, we need to understand where things are, in space, because where matters, proximity matters. It may be that all the spatial effects are relative, but they have to be relative to something. So we have qualitative relations inside overlap that starts to tell us where things are located, for example, in our mental world map, but computers are not as good at dealing with that sort of qualitativeness and ambiguity. So what we do is assign coordinates to the positions of the things that we discern or the things that we sense so that we can give the computers something to do that they're good at. Now, coordinates are also relative, otherwise they're just numbers. That means that we need coordinate reference systems in order to place one coordinate relative to another coordinate, or set of coordinates depending on how many dimensional axes you're talking about. Now, coordinate reference systems are also relative. So they actually need something called a datum, which fixes the frame of reference that reference system is connected with, is defined in terms of relative to mass, relative to some reality that we care about. Of course, geographic coordinate systems are defined relative to the Earth, although lots of ambiguity there in terms of spherical coordinates, in terms of ellipsoids and geoids, the variation from ideality that the Earth actually represents. And then projecting those so that we can work with a flat map that is in most of our imaginations, introduces additional ambiguity in terms of how to do that projection. Whether the United States looks like what we imagine it should look like, or how it actually looks like from another perspective. So the last point is that positions are still just points. And so we can map the points and we can choose points from the geometry, a polygon or a line, place those, and voila, that object has a position in space, has extent in space. But it is actually not telling us that much about the object. You say, okay, so which way it's pointed? Well, I don't know, the points are here. So if we're talking about objects, then we also require not only positioning, but also orientation. And that's what I'll talk about. So we have the need to express for objects, for not just fields and not just geometries, but objects, what's their position and their orientation with 6 degrees of freedom? How are they really situated so that we can ourselves be positioned, so oriented relative to them and everything else around them, everything in a scene, in a room, in the world that a particular application is concerned with can be oriented. So there are several specific applications that we've been looking at. Overlay of synthetic objects in the real world. So we need to know the objectification of the real world as well as the synthetic objects that we wish to place into it. And not only that, but relative to multiple people. So we're also not alone in the world, if sometimes we'd like to think so. And so the need is not only to position and orient all of these objects, but do so in many relative aspects. So relative to observers, relative to situations and scenes. And yet to be able to have a perspective which is truly global and maybe interplanetary. I'll talk about that. Use 3D elements and put them there and have them still be there because they're anchored to the Earth. We'll call it geocentric. So sometimes in manufacturing, it isn't clear, well, why do I need to anchor this to the Earth? I have a room, and then machinery gets moved, logistics extend across the world, and we discover that, yes, global coordinates matter. So here's where this idea of a pose has come to, position and orientation, but relative to what? So we need a consistent frame in order to do that. And the way that we can do that is to define something called a pose. And we didn't define this. We've adapted a concept which is quite common throughout all sorts of virtualization and visualization, graphics and manufacturing processes, but we're trying to make this consistent with this Earth-centric location. So essentially, a pose is the transformation from an outer to an inner Cartesian frame of reference. And so it enables us to say, well, where is that inner frame? Well, it's relative to the outer frame and so on. And we can then define what that frame of reference means. So in this case, we have a frame for the site. We have subframes, a frame for the handle, a frame for the tablet, a frame for the observer. And because they're all related to an outermost Cartesian frame for the site and eventually for the Earth, then we can add in or represent any scale or distance in using these poses or set of poses. So the fundamental description of this is 3 coordinates for a position, 3 coordinates for orientation, whether it's Eulerian or so on. But by defining what an Earth-centric, a topocentric frame of reference is and putting other objects in or next to that frame by using those pose transformations, we can relate these all together to the Earth, to a common frame of reference. The inspiration actually for a lot of this is something called the NASA SPICE system, which addresses the problem in an interplanetary sense. How do we figure out what a camera is pointing at in a satellite relative to the objects in the solar system? And it again involves this extensible transformation between between frames of reference and the ability to concatenate or follow chains of those pose transformations to say, well, so that object over there and this one over here, how do they actually relate? And how is that changing? So the time element in this is very important as well. So definition is the pose captures the location and orientation. It has frame transform, and multiple poses can have a frame transform chain. And a fixed pose is the outer frame is defined relative to an ephemeris object. To call it a geopose is that the ephemeris object is the Earth, and it's using a topocentric reference frame, latitude and longitude, north-facing axis definition, and parallel to the ellipsoid of the Earth. So the geopose ties the location and orientation of a spatial object to the Earth's surface. Okay, so what do we do with that? So that's a nice concept. What's now being developed is some implementation targets. So we look at a basic, 6-number geopose that we can assign to an object and place it anywhere within Earth. But so we noticed for more complex applications, we need to be able to have time sequences of frames and also be able to advance from one object to another object by following the transformations that relate them to a common frame of reference, described as a chain or a graph of poses, or the poses are the links, the frames of reference are the dots, and that graph is what allows everything in a scene or the world or the solar system to be connected together. So this is going to be very useful for a number of things, but really because it will be able to be used within an ecosystem of many related standards that help it to answer the need for agreements in a variety of applications: aviation, aerospace, robotics, satellite positioning, so on. And I've listed some of the ones here, and indeed a number of OGC features, standards. So IndoorGML is one of them in terms of defining spaces as well as routes within indoor spaces. Moving features, which defines in a kind of a neighborhood sense how things are moving around. It's looking at, for example, location information streams from cell phones or cars, and how we measure those things, sensor web enablement. I'll mention again briefly, and some others: ARML, CDB, KML, CityGML, IFC, and so on, InfraGML, also here in ways of representing the objects that we can then define frames of reference for, so that their relative positioning can be described. So where does it fit? Well, here's one way to look at this, is that with sensor web enablement, we can figure out the measurements of where things are, what they are, and what properties they have. Geopose connects those to the common frame of reference, the Earth, so that anything globally can be brought in and related to anything else. We get to what then becomes our augmented, facilitated imagination. OpenXR allows us to then locate those objects to a local stage in a hardware-friendly way, so that we can put those within the local world that is needed for an application. And WebXR lets us then easily, in a browser, take those objects that's seen into the 2D camera frame that a browser might support. So some of these, there's overlap between all of these standards, but there's some sense of an ecosystem and workflow that enables these sort of processes. Just an example, geopose and moving features are for different applications, but they share conceptually many of the same characteristics. And there will be some consolidation, I think, of these, but converting between each of these representations is pretty straightforward. Sensor web enablement. This is not something that one ordinarily needs to worry about in applications, but what it does is protect against many errors of observation by representing the whole process that goes from a stimulus in the world through sensors, sensor models, observations, and then connecting those observations, sensor here, I measure the temperature. What is it that I understand about the world that this is the temperature of? And so creating that workflow of not only where are things located, but what properties apply to them, so that we can get a sense in both physical extent and characteristics of objects in a scene. Okay, there is a temperature alarm. What object is that characteristic of, and how is that affecting nearby objects? And how is that orientation being affected? So it's a part of the puzzle that is in the background, but really essential for not making really stupid errors. I was at some research institution once being shown a radiation sensor that shows its results in a remote monitor, and so they waved a polonium dummy in front of the sensor. The monitor across the room went crazy, and then took the dummy away, and the sensor, the remote monitor continued to go crazy. And I said, well, so what's going on? You know, I'm sitting at the remote monitor, and it sounds like there's a huge problem. And he said, the fellow who was demonstrating said, oh, no, there's a blanking interval. The sensor has a dead time, so it keeps responding when the radiation is gone. And I said, well, but how would I know that? So this is how, when those questions arise, you can learn that. And then XR, there's some detail on how they fit together, but many consonant concepts, and part of the GeoPose work is to work closely with Cronus on aligning these so that they can be used together in the proper circumstances. So, and web agents as well. So I won't go into a lot of detail here, but this is part of that difficult but rewarding process of harmonizing agreements so that they can actually be reused together to address broader circumstances than one alone. Here's another one really out in left field. So OGC works on positioning, discerning, representing objects in space, but then we just say, come up with a global identifier. And one of the powerful ways that this can be used in business, in logistics, in manufacturing, and other applications is by working with another organization that focuses on this identification and tracking issue. So a partnership between GS1 and OGC, we hope, will help to answer both where and what in the circumstances where they're needed. I think that's it. So thank you from OGC, and I hope that you'll both work with OGC standards and work with the standards that OGC works with, and also be aware that we're trying to find the agreements that work for everyone who has spatial information. And so you have a role to help us to understand, as my collaborators in this workshop are doing already, to understanding what is needed from that spatial information and what agreements can really add value in that area. So thank you.
Thank you very much, Joshua. Your presentation was extremely informative, and I truly believe that our audience has appreciated a lot the argument that you very well presented to us, explaining the importance and in the role made by the standard OpenGIS consortium. And I would like to remind you that if we would be very glad if you in the audience have any question, but we also understand that you might probably would like to share your thoughts at the end of this presentation set. So according to the agenda, we should have Rafael Radowski now as the next presenter, but I know that Rafael has some other issues, so some other duty to fulfill and in this conference. So I'm wondering if Rafael is with us already. Otherwise, I would suggest Johannes to start with this presentation, because as I said, I know that Rafael is involved with some administrative duty here, is involved in the as a workshop organizer also in another session. So probably Johannes, you might be so kind to start your presentation. Please let me know if you're ready.
Oh yeah, I'm ready. So just share my screen. Just give me a second. And here it is.
Okay.
Yeah.
Thank you, Johannes.
It's my pleasure to be part of that. Okay, hello everyone. My name is Johannes Scholz. Let's say assistant professor, hopefully soon associate, at the Institute of Geodesy, which deals with geographic information systems and science, remote sensing, navigation, satellite geodesy, and all that stuff. And I'm heading the geoinformatics working group or research group there. And well, I'm pretty happy to share some stuff that we've done during the last couple of years. So basically, what we are looking at is the work of a PhD student of mine who has finished his work or his PhD in 2018, and some other let's say master thesis that were done in that particular area. So basically, that's the table of contents. So that's what we are looking at. So first of all, I'll give you a short introduction and motivation. What's ahead of you? Well, here I put some relevant literature into the table of contents, but I guess we can skip that for the sake of time. So we just move on to the indoor space and how a semiconductor manufacturing facility looks like. And then we are about to see how we modeled our indoor space. So basically what we've done here is we used some ontologies in order to model indoor space. So we have like a semantic model of the indoor space, and this particular semantic model is then used together with an epistemological model to let's say to work on some use cases and to let's say analyze spatial-temporal data that we have in terms of manufacturing data. I will also have a look at or I'll show you some details of our implementation of the graph database. So basically we implemented all the data storage not in a relational manner. So we created a knowledge graph. Basically, that's the ontology and the manufacturing data that we had at our hands. And based on all that, you will see how we conducted some use cases. So basically, it's a little bit of geo AI. I mean, it was a little bit ahead of time. So nowadays we're talking about geo AI, but at the time, this term wasn't, let's say, in the first one is affordance-based navigation, and we'll have a look at that, and some incident analysis, which is well, pretty necessary, or a pretty let's say use case that's pretty necessary in Industry 4.0, and some identification of bottlenecks in production lines, basically. Yeah. So that's basically it. Well, let me start with that one. So I know everyone is spending more time of the day indoors. So when there are some let's say pretty famous studies around, some pretty famous papers around the deal that that basically state that we are spending like 90% of our day indoors and only 10% approximately outdoors. So the issue is that as humans, we tend to have time indoors and outdoors, but the problem is, according to those studies, we are spending only like 10% of our time outdoors, and the problem is that most of the geographical information systems were designed for the outdoor world, let's say outdoor space, and some colleagues, several times cleverer than me, they stated that the problem is that we've designed everything for our outdoor world, where the geographical information systems come from, let's say. So basically, it started off with landscape architecture, if we go back to the 60s and 70s, but they're not pretty well designed for the indoor world. So, and that's surely a problem that we had to address in our community, and also the OGC. They did pretty good work in that particular arena, and also the scientific scholars around those people did quite an amazing job actually to mitigate those issues. Now you might ask why we were also so interested into the manufacturing environment. I mean, that's not the obvious use case, let's say, because like most of my colleagues in the geoinformatics departments, they were up to modeling, let's say, shopping centers or office buildings or stuff like that. But we were particularly interested into let's say a more complex and more let's say difficult environment than classical office buildings. So I mean, it was like a little bit of a personal endeavor as well, that we had a connection to a semiconductor manufacturing company, and but the issue is that those companies are like the clean rooms that we have at our hands there that we're working with. They differ pretty much from ordinary indoor spaces, and that's what was pretty appealing to us, and we thought this would be pretty interesting. Well, and in those clean room environments here, basically we have two items that move or that are moved indoors. That's basically that are the humans that move, and we have the production assets that are moved by humans in our particular case. And we had some questions and some overall objectives that we're facing when we're starting all this. First of all, we were about to ask ourselves if we can describe this manufacturing space with the help of an ontology, and that includes also some manufacturing, let's say, peculiarities in the indoor space, meaning that we need the machinery, the devices, the manufacturing devices. We would also need some manufacturing furniture. We would need to model all the humans, the human movement, the movement of the production assets and all that stuff. And we're also curious about if it's possible to somehow support wayfinding decisions of humans. That was pretty a hard question, actually, if we can do that, especially if we can utilize ontologies and the affordances that are the results of the ontologies for wayfinding for our production assets. And well, we also had some objectives of the semiconductor company at our hands. It was like we would like to, or the company would like to support operators in the wayfinding tasks in the facility. And we'll see in a sec why this is pretty important actually. The second objective was that like the pickup and delivery tasks of production assets, that's pretty a complicated task because you can get pretty easily lost in that particular manufacturing space, and all production assets look the same, and it can get quite messy when you're looking for a particular production asset and you have no clue where it is.
I'm a researcher at
And it's standing on a shelf with like 200 other black boxes. That's pretty, can be a pretty nasty task. And the issue is also that some production assets need to be delivered pretty fast from that. Pickup and delivery can be pretty crucial actually. So, and in the end, the overarching task was, or the goal is, and still is, they would like to have like a autonomous pickup and delivery of those production assets, which is still not fully reached actually. So all in all, they would like to have an increase of the efficiency of the production line. Okay, so starting with the indoor space, so it's a rather old picture of the company. So we have like 5 production halls, and what you can see also is that one production hall is a little bit bigger than the other, that's left one, and so that means that we also have manufacturing halls located at different levels, at different vertical levels, meaning that we also have vertical transportation when we change a hall, and all that stuff looks like that. So inside the clean room of the facility, it looks like that. So it's a pretty narrow space. So you don't have too much, let's say, space to move around or to transport or to have some storage facilities around you. So that's pretty secluded, a pretty secluded space. You have to be pretty efficient in there, meaning so you have not too much space to waste actually. And one of the issues is so you have the production assets, which are the black boxes on the left lower corner. So you have all your wafers. So that's basically silicium wafers, and in the silicium wafers that are the base material to create microchips, basically. And all those, and one of those boxes, or one of those set of silicium wafers is put in such a box, black box enclosed, so that it's really safe from environmental hazards. And that's basically it. So what the operators move around are those black boxes, basically. So that's basically how the manufacturing facility looks like. And here we have collected some characteristics of those manufacturing environments, of those semiconductor environments. The issue is that we have a high number of production assets in the manufacturing hall, and there's no clear, let's say, production line. So it's no line where the production assets enter the hall on a single
Hello,
point
my
of
name is
entry,
Bruno Simões.
and
I'm a
they have
researcher at Beacon Tech
defined
Foundation.
steps from start to finish. Problem is that we have a number of different production, let's say, production types or asset types that are produced at the same time in the same environment. And so they have different routes through the hall. They have the production assets have different degrees of completion. So meaning you can have a product right at the start of the production and a product that's pretty finished sitting right next to each other in a storage shelf. So that's pretty complicated actually when you try to handle all that stuff indoors. We also did some analysis of the movement of the production assets indoors, and we found out that those production assets move several kilometers in that complex process chain. So that's pretty heavy actually. Several kilometers. If you look at the manufacturing facility that we're looking at, it's basically a 100 by 40 meters production facility, and that's basically it. So if moving several kilometers in that production facility is you could call it inefficient, or you can call it, I don't know, whatever you would like to, but it's not the most efficient way to do all that. Just for clarification, every yellow block here is a single manufacturing device, and the green network is the movable space, or let's say navigation zone where humans may navigate or walk around. And that's basically it. So that's one of the production halls. So how did we model that particular indoor space? So before we started all that, we were having a look at literature, and there were several approaches around that we could use basically. And I don't want to go into too much detail of all that, but basically what we did was we modeled the indoor space with the help of an ontology, and we described all the interactions between the indoor space, production assets, manufacturing devices, and humans with the help of affordances. And that's similar to the approach of Mike Warboys. So Mike Warboys is one of the bigger scholars in our area. So that's one of the things that he discovered, or he invented basically, and we made kind of use of that and did some alignment to his approach as well. So I just want to give you an impression how the ontology looks like. So we have like several top-level elements, which is, for example, production units. Then we have the access nodes, which are linking the indoor to the outdoor space, or the outdoor to the indoor space, or indoor to indoor space. So you might ask why indoor to outdoor and outdoor to indoor is different. In that particular arena, semiconductor environment, you always have you cannot enter or leave the clean room at any point of the building. That's basically not possible. So you need to have specific entry points and specific points where you can leave the building, or the indoor to indoor space is necessary because you can, when you enter or when you change the clean room class, cleanness class of the air that's in the clean room, then you have a specific shutter between those two clean rooms basically, and that's where you need a specific point to connect those two clean room environments. Then you have corridors where you can move around as human. You have some barriers which impede your movement, and you have like some navigation elements around that you can do the navigation task if you want to. And we already published that in 2014, which was pretty early for that. And basically, the ontology looks like that. We modeled the ontology with in OWL and the ontology web language. And you say that all the stuff that we did here what is related to specific position. So that's basically a spatial-temporal ontology that includes the spatial and temporal domain. And yeah, that's basically our, let's say, semantic model, how we model the indoor space. Yeah, and based on that ontology, we somehow tried to come up with an approach to somehow model how we can, let's say, simulate the movement of humans or production assets, so that we can somehow support the autonomous movement of production assets. And our approach was like the following. So we tried to come up with artificial intelligence. You could name it like that if you want to. And we were about to say, okay, what does our environment tell us of what we can do with it? So that's basically the concept of affordances. So let's say, for example, a stairway tells us that it's a stairway, yeah, and the production asset knows by itself that, for example, a stairway is not the proper way to move over, for example. So you can move over a stairway, for example, with specific production assets, but with others that's a pretty no-go. So it's not possible, or you shouldn't. It's not advisable to do that. And that's basically what we did. So all those affordances are like a combination of the environment, so the properties of the environment, and also the capabilities and also the properties of the agent or the movement feature that's about to use a specific environmental object. So what we did, for example, we created an epistemological model for like the operators and for the production assets. I just put an excerpt, a small excerpt here, what everyone is capable of doing in the environment. And this list of affordances helps us, or helps the agents to autonomously detect what's a potential path they can use, or what's a potential path or potential area that shouldn't be visited, or a path that shouldn't be used at all. So that's basically why we did all that. And this affordances can be generated in a fully automatic manner based on the ontology. So in order to somehow store that particular piece of knowledge, or that digital twin, let's put it like that, of the manufacturing environment, we somehow tried to come up with a approach that natively supports all that. And we, in 2014, 2015, we tried to somehow come up or look out for technologies that helped us in that particular endeavor. And graph databases were like a pretty natural fit in that, because we migrated our OWL ontology into the graph database, and migrated also the manufacturing data, their semantic annotation, and all that stuff into the graph database. So basically what we came up with, that we had some historic manufacturing data, some attributive information, some future manufacturing data. So what should happen with all the production assets? So which manufacturing steps are still ahead of them? All that is based on spatial information and the indoor navigation ontology in a spatial graph database. And basically it looks like that. So we have like the current manufacturing data and the spatial data, and also the indoor navigation ontology together in a graph that's connected with each other. So that's basically a geoknowledge graph that we're looking at here. And because it combines like the abstract ontology and the instances, the data itself, which helps us to analyze this data in a proper manner, in a proper way. Okay, moving on, we try to somehow make that or use that in particular use cases, and to somehow analyze our manufacturing data with the help of those semantically annotated data that we have. And basically, we're looking at 3 different use cases. The first one is affordance-based routing. So that's the key use case, let's put it like that, because that would somehow help us to make the production line a little bit more efficient and to somehow support the autonomous routing and autonomous movement of the production assets. And we do that with the help of the affordances that we did. And basically what we do here is that the production assets, they basically look into their own data sets that they have, or in their own data that they have, and they look into what manufacturing steps are ahead of them. So they know which production steps is required, or which production steps are required. They know which suitable machines are there to perform the next production step. And they can also determine where the machine basically is located. And the crux here is that there's not a single machine that can perform a particular manufacturing step. It can be a set of machines that are geographically dispersed over the whole manufacturing plant. So you can look for like the best quotation marks machine, and you can also look at or determine the best route to that machine. And that could include, for example, the safest routes. So the avoidance of any dust, the avoidance of, for example, bumps on the road to that particular machine, because bumps are a killer for those silicium wafers. Because if you move over a bump and the bump is too hard, then those wafers might break, and that's pretty costly actually. So all that particular best routes can be determined for each particular production asset. So because each production asset has its peculiarities, and in the end, you can navigate to that particular machine. And that basically looks like that. So it's just a small graph or a figure depiction of how that basically looks like. So we are looking at several machines, then a start and several endpoints, so meaning some candidate nodes in the network that are the candidates where the production asset might move to. And then we are looking at the routes, and we are looking at basically from the candidate machines backwards to the starting point of the route. And then we look which of those candidate routes are the best ones, or are the ones that can be traversed based on the affordances of the route. So if the route is basically suitable for a particular production asset or not, and that's basically what we're looking at. And with that help, you can basically prune several edges out of the network, which makes your life pretty easy, even if you have a big network, even if you have a huge number of production assets that need to move around and all that stuff. So you make your life pretty easy from an algorithmic point of view. So our second use case here was incident analysis. And in our case, an incident basically is like an unplanned event that somehow hinders the completion of a particular task, basically. So an incident could be a failure of a machine that you desperately need, or like, for example, a specific airlock, like maybe a point where it can move from one clean room to the other might be broken, or like an elevator might be broken, so you cannot vertically transport your production assets anymore. And or maybe you have a filter that's broken in the clean room environment and stuff like that. And the problem is, in such a production environment, you would like to somehow detect those incidents pretty easy, and you would like to see where the incident has its root cause. So our use case here was like, we would like to detect of a malfunctioning air cleaning, and that's basically what we're looking at. So, and based on that, we did some, let's say, we did some semantic analysis based on that. So we tried to somehow see which assets were affected by that particular malfunctioning air filter here, and then we looked at which trajectories somehow crossed a specific area in the production line, basically. And then you see which other ones could be potentially affected. So which other manufacturing facilities or production assets could be affected, and then you can have a particular look at them. And the third one was bottleneck analysis, and so the identification of bottlenecks is a key issue in the manufacturing environment. So we basically try to come up with an analysis of the data and see where bottlenecks are, where where the assets were standing or waiting for a longer time than necessary. And we have like a moving average implemented here, so you can easily detect where you have some problems in your manufacturing hall, where the assets are waiting too long to be processed. So maybe you should rearrange something here and see where you could somehow rearrange your machinery, your devices, where it should come up with some extra capacities to produce, or some extra manufacturing capacity in order to mitigate those bottlenecks here. Yeah, so that's basically it. So that's basically what we did. So we tried to come up with a model of an indoor space with an ontology and a geoknowledge graph. We tried to come up with basics that are necessary to somehow that are necessary for location-based services or location-based devices that can be mounted on trolleys or mounted on people, let's say, or that the people can take with them, so that they can easily identify where they are, where the next tasks are, and stuff like that. Based on the things that we did here, on the findings, you could somehow support autonomous pickup and delivery of all that assets, and you can also support extended reality and virtual reality devices with a particular indoor localization service, for example, ultra wideband, that should currently be installed there. Yeah, we tried to somehow integrate all that in a graph database, which is a pretty nice issue here. And with the geoknowledge graph approach, basically you're able to do a pretty high level semantic and spatial analysis of all the data that you have, which helps to help you with your decisions. And before I leave, or you leave, whatever, either one. So we are basically having an ongoing survey with our colleagues that are present here in the workshop on geospatial data and geographic information systems and smart manufacturing. So, and we cordially invite you to participate. So it's one of the base support us and take the survey. And so I'll just leave it here and say thank you for your attention. And if you have questions, just drop me a line or just unmute yourself. I'm happy to answer your questions. Thanks.
Thank you very much, Johannes, for your very exhaustive presentation. It was really a pleasure to see how you, from a very specific use scenario, you really did something extremely interesting. I'm very curious to keep our conversation also later on in the question time session, or when we are going to all together try to collect the finding of our presentation. So I believe Rafael is now with us. Yes, yeah, and I would like to remind, we still have 2 presentations, so we are still on time, but if we would like to have 50 minutes to collect our findings, then I would suggest Rafael and Bruno not to take more than 50 minutes each of you for your presentation. So, Rafael, I think you are super familiar with this platform. So I'm asking you to share the screen and please go ahead with your presentation. Thank you.
It's spent now, I don't know how many hours here.
We can hear you.
Yeah, 1 second. So, that's it. Correct. I cannot switch into presentation mode. If I do it, I don't see myself anymore. Everything is black and dark in my end. Okay, sorry that I missed the other presentations, but I had another talk in another workshop, and I have to teach in an hour. That's the other thing. Okay, my topic here is visual indoor positioning for workplace augmented reality support. I'm actually not really going to talk so much about indoor positioning. I'm going to talk more about how do we make it accurate, or how do we prevent the typical mistakes that happen in a situation like that, where we actually have or adapted a very popular solution to that from a technical point of view, but it was unclear when we actually implemented that whether or not we can use the solution with those landmarks that we have. So the solution that we have is basically landmark-based tracking on a factory floor, and so usually when you use landmarks, you use very distant points, something that's a door, a building, or so on, something that's very great. And we want to navigate this landmark on a factory floor level, and had to figure out, okay, what actually can we use for that? And it actually work if we use those types that we decide to use as landmarks. And so that's more a small and big report. I also want to point out the problem that we actually have when we do augmented reality on the factory floor. And I will do this here on a very underspecified high level. So I just removed all the brute math and all algorithms. If you're interested in that, contact me. I can provide that's not the problem. But I thought to focus here on the discovery problem, I don't do it. So let me switch to my first slide to actually know the scenario that we deal here with. Okay. Yeah. Okay, so this is a typical augmented reality scenario that we're talking here about. So when I do augmented reality, a lot of my partners that do augmented reality are interested in training. In this case, it's here assembly training. The assembly training typical scenario, we work with say like a HoloLens, you look through the HoloLens, and you see those screenshots show you that you see digital content shows you or conveys instructions. When I do those things, I usually also assume that some sort of camera around. So you see this in its rendering at the right here. Oh, you don't hear me well? Okay, I can move closer. I'm not sure as people said before. I can move closer to my microphone. I'll try. So when I look, I usually assume it is some sort of, I have some sort of environment camera, like here in this rendering, RGB camera. Here this is the workbench scenario. The camera observes the workbench, and the camera observes all that the user is on the workbench. So we can use the data to track paths like this piston motor here, and position, and we can superimpose objects. The next video will show you how we can use that. So this was something that we did with one partner. It was a project. It's actually what we did is actually over, but we start a new one. And but this was our initial scenario. So the user wears a house, and the user goes here from assembly station to assembly station and must perform some tasks. This HoloLens will show in the graphical information. Something like here, like the table, in this picture on the lower left, goes tracked and there's a video, the HoloLens talks to the user and gives this guy here information, and you see the graphical widgets actually display what the person has to do. So at this company, they have assembly station, training station, and people, they take those cards and they send them from assembly station. Every assembly station can cater products. They scan the code first, if they know which product they have, then they take the instructions. So behind the user, there are two connections. Actually, they track the entire environment. Oh no, they generate data that allows us to track parts in the environment. So they're actually tracked, and when I talk about tracking, I talk about freedom tracking. We can track the position of some relevant parts. We don't do all of them, just for a few which are relevant for tracking. So the information. This person is not a student, this person is not a professional actor, so he did not really focus much on my video and more on assembling the part. It's really an operator who works for a company. And both parts here right now. So the graphics, the model may appear a little bit off. That is just the issue. So the HoloLens has its own image compositor renders the view, and this image compositor uses the sensor camera. The graphics renderer uses one of the right or left rendering. That's the outcome we have. See if I can move it forward because I want to go through the track part. So now you will see the problem already that we have. So now we see where the problem comes from. So takes now this part here and this table, and so you see that the yellow part looks a little bit rotated. It doesn't 100% align with the table. It's off. It's rotated. It's on. We for a very long time thought it's not just a calibration issue. We were actually right with that, but we did not. The user company didn't calibrate the system right, and it actually turns out this happens when you use the system for a while. Then the coordinate frame actually moves away a little bit. So let's see. And let me show you this video. So this is basically the upper shows you the part again. This is just now a lab video here, and this is interesting from the data point of view. So something in the start, basically a path that moves through a point. Green object is the graphical representation of our reference model. If we use the tracking, it's some sort of a model-based tracker. And you see that the first image here, and the first moves the object perfectly through the world. So, I will just skip the next one. Fine. So just a brief overview of how this entire tracking approach works. As I mentioned, assume that we have a room camera, that we have somewhere an environment camera, or multiple environment cameras that allow us to. Oh, I'm cutting off. I don't know what it might be my internet connection. I'm cutting off. Maybe I just have to turn around and you basically listen back. Yeah. So it's just a very unspecified approach here of how we track. We use that we have an environment camera, an RGB camera, a depth map to generate point cloud data. We distinguish the detection step and post estimation department step, and then we have an approach, and the entire approach is model based. I will not talk about this in detail, but as you saw in the video, use this approach here to generate a 6DOS pose of every object you want to track. It's basically, matrix that tells you what it is. With respect to a coordinate frame, it's fine. So there's not a problem that I mentioned. So for the point with a user with a connect, it's basically a connect user with a connect through this point cloud coordinate frame. Problem is that the connect and our tracking coordinate frame are actually aligned, or these are two individual coordinate frames. One is a connect coordinate frame, one is a tracking coordinate frame. The entire render here indicates that I will not put detail here. This is also not really complete, but it shows you the sections. This part of D here shows you the connect coordinate frame, basically coordinate frame D, and we have our camera frame, basically coordinate frame C. And to be able to do something that we saw at the very beginning, we need to be able to align those two coordinate frames. We need to be able to align the frame of object, of the fact object, and the coordinate frame to connect the HoloLens. The HoloLens is something what we call markers or anchors. These are basically duality anchors, something like this here. There's on the left this anchor bubble, this one here. You can actually put them into the world, and all objects are rendered with respect to this anchor. So we have to align those things. At the very beginning, this was an anchor, and if those coordinate systems are aligned, render everything perfectly. So problem number one is they don't stay perfectly aligned. After a while, those things move apart because we have errors, we have tolerance errors, detection errors, and we have post estimation of liability. We have a probability in our post estimation. All of those are errors. So those coordinate frames, they drift apart after. So the second problem is we do not only have one anchor, or we do not only have one coordinate frame. If you have a company and you have individual stations somewhere around in your area, you basically generate an individual coordinate frame for every station you have. You might have here gets a coordinate frame. You might have the 36 frame. You have other equipment here that gets the coordinate frame. All those coordinates are individual coordinate frames. They exist in global coordinate frame. All of those are aligned to a map. And this map is basically an environment map, but there is no global reference for that. It's also not really feasible global reference in reality. So, and that's the second thing. We have more than one in the drift part. Now let me reduce this again to two of those. What happens if we have just two of those? So this is our simplified scene. I hope you can see this here. This red frame here. This one here. This is target we saw before. let's just not assume the frame is actually a frame, it's a graphical model. It's a 3D model, it's an instruction model. So this instruction model is basically rendered from this point, that's its origin. Assume we place the anchor here. This is now another 3D model, or it's not this 3D model instruction on that, just a random part, which is anchored to this anchor here. This part here, anchored to this part here. And it's great to move this. Okay. Yeah. And now let's see what happens if the user has the HoloLens. So the HoloLens has its own environment, its own training environment, framework, which is technically some sort of semantic level, but there is no math or there is no signal or anything. So we move, and now let's assume the user takes this part here again and puts it on top of the other part. The object could be just a 3D model or another part, which is true or an end cap or something. The model is rendered with respect to this anchor here. So the anchors are usually fixed. They are fixed in and usually don't move simply. So now let's assume from this part to this part here. So what happens after a while, it doesn't happen directly, it doesn't happen instantly. But at one point we get some drift into the system. It just say after all other things. And if you move further, and you get more tolerances, you see this here, this frame completely may move completely away from this frame. And that's what we saw, that those some initial development, the coordinate frames don't stay where they are, drift away from time to time, and then they are completely at a different page. So what is the typical approach to deal with that? It's based landmark, key-based landmark tracking. So you have known landmarks in your world, and you actually use them as fixed points in space, and you use them to track your map. So the question is, what can we use in a factory landmark? That's not the factory floor that we actually use. It's just a random picture that I Googled because I cannot show you the factory floor. But it's so we walk along the floor and we're looking for, okay, what can we use here as landmarks? And it's actually quite complicated because nothing looks like the typical landmarks you usually know from computers. And we take us about, okay, how do we close, how do we close different other things. They have their outdoor landmarks, indoors, they have sometimes really doors, hallways, or they're really different things. So we look into those boxes here. They have all those electric boxes. And our question was, can we actually use those as landmarks, measure their position with the machine they're interested in, where we want to render our data, can we use those actually as points to correct our data, to correct our data again, so to move the graphical object back in the map. This was the basic idea here, and that's again just an underspecified measuring of how it works. As I mentioned, we have here a map, which is a tracking approach again, and we get here a post tracking. We have here a map. Map means here actually we maintain the location of our tracked points just as a digital data set with a probability assigned to it, and so on. So, and then the new part here is your landmark detection. This text landmark with boxes here. This is what we hope is in our lab far. And then we can work on the map correction and update our map. So does it work? Yes or no? It works quite nicely. There are some difficulties, but so far it works. So post tracking, the error. What is that? That is our error. So for our tracking system, we either use a Kalman filter or time validation network that gives us probability as our pose as a hidden state, depending on the probability of the previous transformation and the probability of our transformation. We usually compare this with a linear model. With a linear model, actually can output an error and tell us, okay, how is this function actually that we have? So, and that's our data for our detection. So after a while, when you always maintain probability values and the observation gets quite bad, then at one point you deviate from doing a motion model. And we trigger our landmark detection. Not always landmarks, that's quite computation expensive, and not use this on the HoloLens. So landmark detection, I believe I missed that. Yeah, landmark detection is something HoloLens has to do with the HoloLens when we notice, okay, the entire mark part flips away from all our coordinate frames part, then we basically tell the HoloLens, okay, try to figure where are you back to your tracked environment. Yeah, we basically check when this error is too big. There's a human set threshold somewhere in between right now. And yeah, where it's coming from is a comparison model. When we see that at one point, then what we do is actually, we are here right now in T0, which is our current state. We trigger a key-based landmark detection in one step. So the first thing is we cannot do this immediately. We have to do it in the future because the connection is a network connection, and to do this with a HoloLens to get the picture back and so on. At some time, we basically have to offset that. And so that's what we do. We then at one point ignore all the data at one point and just say, okay, let's do this part. We did this so far with 2D feature descriptor in our lab here. You see here we use some areas in our lab, like those posters and other ones that we have as basically we put some crypto database and run them on the host system, not on the HoloLens. So we get the pictures back, we run to a host system, and we send the data back and correct our local and correct the map. And that's why we have to do this in this to actually correct for any drifts. How it looks like, this is now a lab experiment where you actually see that. I'll point out when you see the correction if I don't miss it. You can see at one point the entire object rotates, and then at one point it jumps back. And it's really like the information here is a little bit latency. Yeah, it's still all good a latency here. You see when we move it's so good and then go back. This was a trigger. I moved my head. One of the problems to get this a whole and move your head. So now we rotate. Now it starts to drift away here. Yeah, now it rotates. Yeah, now it's gone, and then it goes up, jump back. That's the correction. So it basically, and then it stays put again. Now you see it's on top again. So how does it look in data? That's not hard to see. It's what we see here is a comparison of those two passes. That's not completely real scientific experiment, but we still figure out how we can really measure. So the red part is basically the part, just an XY plane. So the person moves the part around, and then the blue dots is the graphical. And perfectly, they should always perfectly align. See here sometimes those blue jumps here on top. And these are just random jumps. They happen time to time. It's not critical. These are jumps, they are not so critical. In general, we want a very aligned here. And that's what we want. So what you need to watch here is this one here. That's basically a data set where our two models, our graphic model, are completely off from our fact model. And I mentioned this is not completely, not an experiment of position here. The graphical position is actually a measure for its position. So we measure, we know where the HoloLens is, and then we actually calculate this array here, or this here. But that's how we can see this in data. And operation gets it actually back, and it actually jumps back. So that's where we are. As I mentioned, it works correctly. There are some drawbacks with the entire method. One of the drawbacks is we have planned for the future right now. Every time when we drift away, we have to ask, okay, when can we reset the part? If we move the part in between, and that's why I actually didn't move. You saw that right before it snapped away, very, very slow. So if we move the part, then basically the part triggers the correction, then we can trigger the correction, and the correction is based on doesn't match anymore. And when it takes so much, you basically jump from one error into the next error. It's a process problem. It might be better with something too. We have done this so far also on a very small scale. So you saw Mentors lab setup. This is actually the actual training setup where we have tried this so far. We haven't planned and haven't done this on a factory floor with module map. That's one step where we to move through a factory floor, through a tracked factory floor. We plan for 4 connects there, take multiple of those parts and multiple stations. Do some, I believe, dummy instructions there, tell people what they need to do, and just see how it works and how we can recalibrate our entire system closely. The entire system also solves another problem. Initially, very first prototype, and you didn't see that in the video, we used the marker, a visible marker to align the two coordinates. And the system also now gets rid of the marker because we use some sort of element, which is actually a quite nice feature. Actually didn't have at the beginning. And that's thank you.
Hello? Rafael, can you hear me?
Yeah, I can hear you.
Okay, great. So thank you very much for your presentation. I'm sorry if the quality of the sound was not the one we expected, but your presentation was extremely informative, and I think that our audience had the chance to catch most of the extremely interesting research activity you conducted. Now, without any further hesitation, and I hope that Bruno is with us, and I would be very happy to invite him to share also his presentation in the screen. Bruno, are you with us?
Hello, Raf. Yes.
Oh, great. So it's really the case to say, last but not least, you are going to complete this set of presentation in the all of them aiming to provide and disclose advanced research in the area of augmented reality in the context of Industry 4.0, and how this application domain can eventually benefit also in exploiting geographical information. And I believe that you also enjoyed a lot the presentation made by Rafael, because we also experienced the similar challenges in the research we conducted together, Bruno and I, are working together in this domain probably since more than 10 years. And I'm happy to introduce you in this workshop and also presenting the activity that you are conducting in BConnect in Spain in the domain of digital twin. So please share your screen and go ahead. You have plenty of time, 30 minutes, and thank you for being with us today.
Okay, thank you, Raf. So it is indeed a bit late here. So a few hours ago, I recorded a presentation just to avoid any issues. If it goes well, then it will play. Otherwise, I will present it. Okay, so maybe Philippe, if you can. Hello, my name is Bruno Simões. I am a researcher at BConnect Foundation, which is part of the Vasco Research. I joined the group of advanced manufacturing, and I've been this. Well, I don't have audio. Do you?
No, unfortunately, we couldn't hear your voice.
Yeah. So
I think that probably we have to switch to the traditional mode.
Yes. So let's. Hello, my name is Bruno Simões. I am a researcher at BConnect Foundation, which is part of the Vasco Research Technology Alliance. Over the past years, I joined the group of advanced manufacturing. Hello, my name is Bruno Simões. I am a researcher at BConnect Foundation, which is part of the Vasco Research Technology Alliance. Over the past years, I joined the group of advanced manufacturing, and have been working on virtual engineering techniques. My name is Bruno Simões, and I'm a researcher at BConnect Foundation.
For a second, it was okay.
Hello, my name is Bruno Simões. I am a researcher at BConnect Foundation, which is part of the Vasco Research Technology Alliance. My name is Bruno Simões. Hello, my name is Bruno Simões. I am a researcher at BConnect Foundation, which is part of the Vasco Research Technology Alliance. Over the past years, I joined the group of advanced manufacturing, and this presentation. Can you hear me? Hello?
Yeah, we hear some of what the registration says, but at a certain point we don't hear you any longer.
Okay, so let's try again. So my name is Bruno Simões. I'm a researcher at BConnect Foundation, which is part of the Vasco Research and Technology Alliance. And in this presentation, I would like to talk a bit about the concept of digital twins. My slides are auto-playing. Second, sorry for the convenience. Okay, let's give it another try. Well, in this presentation, I want to talk about the concept of digital twins and the experiences that we have integrating them into Industry 4.0. But the most important, I would like to talk about some of the challenges that are associated with digital twins, as well as future directions in this area. This includes, for example, the Geo platform for digital twins.
Bruno, I don't see your slide. I'm sorry. I see the I see your screen, but I don't see the slide. I see just the PowerPoint application currently. Probably you are going to present mode, but
Do you see the presentation?
I don't know if it's just me, also similar situation, and also, no, I don't.
Yeah, it looks like the share screen is frozen, at least for me.
Yeah, same for me. Try to unshare your screen and share it once again.
Is it visible now? Probably not.
No, not visible.
But try the screen behind you, smaller one, but we can all zoom in.
Oh, that does not seem to be my screen, the one being presented. Maybe I'm not sharing my screen.
Yeah, that looks better.
Yeah, I get like so. Do you see the slides being presented or not?
I do see the slides.
We're seeing the presenter view, not the presentation view.
Maybe I should switch to.
I believe we always see the main view, so you have to put your presentation to the main view of your main screen.
Then change the display to clone. Maybe that will fix the problem.
Okay, now there is one screen. Okay, I was saying that. Okay, great. Now it seems that your presentation is on the right screen.
Okay, well, I didn't understand exactly what I did, but important is that it works.
Yeah, great. Okay.
So
Okay.
I divided this presentation in 4 main sections. The first is I'm going to provide a definition of what digital twin is and its role in Industry 4.0. Then I'm going to describe a bit which are the challenges of integrating and creating digital twins. And as the last, I will talk a bit how we can further develop this concept and which are the future research directions that we'll take in the manufacturing sector. So I will talk a bit how the concept and definition of digital twin changed over the last years. It started probably more or less in 2002 when Greaves introduced it for the first time, a digital twin as a conceptual ideal for the product lifetime management. In this vision, the digital twin would describe actually what a potential of actual physical manufacturing product would look like from both the atomic level to the geometrical level. This vision was oriented mostly to mirroring the information that we get in the physical space. So the result was a digital product that would provide a similar experience with the same data and reflecting the current states of the physical product. Later, in 2012, NASA introduces with the potential for simulations. So they integrated a simulation of a system used to mirror the life of an aircraft based on the best available physical models, as well as sensor updates, fleet history, data, and so on. So this extended the previous vision of a digital twin with the fact that now all that data can also be integrated with simulation algorithms and models, and all these models can operate in a timely manner. In the last 4 years, the manufacturing industry started to integrate the new technologies such as virtual reality and augmented reality into their digital twin solutions. Earlier, it was difficult for the companies to adopt such capabilities due to the high computing storage and the bandwidth cost. But now that the costs are lower, they start enabling communication technology where leaders to combine this technology with operation systems and deliver a new type of experience that not only can represent the product, but can also be used to understand, predict, and optimize the performance of the physical product over its entire life cycle. So here, this concept starts to shift towards a synchronized representation of both worlds, so the physical and the virtual one. So a digital twin can be identified by 3 main pillars. The first is a physical product in the real space. Then we have also a virtual product in the virtual space, and the connection of data and information, which ties together these 2 spaces. So we get on the left side, it's the real shop floor, and on the right side, we have a digital twin, which is a digitalization that in this project we created for the shop floor. In this case, data that comes from the machines, which includes production data, raw sensors, go into the digital version where the company can apply simulation data to optimize the process. Later on, I will explain a bit better with other cases how this really works. So one could describe at the end digital twin as a way to create an experience of a product in a digital world that can be indistinguishable from the physical product experience. It provides 2 important capabilities. One, it allows the humans to understand the product as well as its data. So it's a way actually to manage data associated with the product. And the second one is it provides a baseline for data analysis. And this data analysis is based on the best available models for the computation, as well as data from sensors and historical conditions that most of the times received in near real time. So the application of digital twins has been observed in a several number of domains, but has mostly been associated with industrial production. So we have heard a lot about examples on smart factories, production lines, or at low level individual machines, which can be, for example, robots and production or manufacturing devices. However, there are also now expanding areas that include, for example, logistics or construction, which is less important for this talk, as well as infrastructure and services. So in the case of manufacturing for industry, the digital twin has the ability of real-time control and optimization of the product and the production lines in the manufacturing environment. So companies can use it to predict the behavior of the machines, equipment, or manufacturing processes. And this is a tool that then can be used to optimize the processes and detect problems before they occur. Another important enabler with this technology is servitization. So companies can now start to deliver and deploy services that allow third parties or other stakeholders to also collaborate and contribute to the manufacturing process. What we have here is the digital twin of a plant, and inside this plant we have other digital twins that apply to each of the robots that we can see. For the robots, the data is collected and they can perform simulations about the time and how the robots can assemble and collaborate together in the shop floor line. Digital twins are also growing in different domains, as automotive. This is the image of a Tesla, so we can see that a lot of information is also collected about the car. The car has a number of sensors that allow to detect and recognize objects around. And by creating this digital twin, it allows the manufacturers to anticipate maintenance based on the data that was collected during the lifetime, as well as use that data for continuous improvements of certain features of the vehicles. In the case of the Tesla vehicles, we are talking mostly about autopilot features and so on. Another application domain is in the aerospace, probably where it was first used or mostly used. So this is the example, an example from Boeing of a turbojet. So data could be collected, which would include temperature, vibration, air quality, as well as other simulation data, and all be used to predict blade grades or suggest the right time for maintenance and shutdowns. So merging both the physical airplane with digital data in a more seamless communication platform. Another example is the use of digital twins in the energy sector. For example, in the case of wind farms, the wind farms can have its own digital twin that collects, again, real-time data from the sensors, but also can collect data from external services like weather forecasts and so on, and perform simulation and stress models in order to suggest actions to be applied to the physical model, which can include, for example, changes to the production, as well as preventive actions to account for damage or cumulative damage. So we reached the half of the presentation. Now I will describe a bit some of the challenges that we have been facing in this domain. There are 5 topics. The first is about engineering problems, then commercialization problems. The third is the technology-related challenges. Then we have a problem that is pretty much everywhere. That is the problem of data. And then finally, the topic that I will expand a bit more, the other problems regarding the digitalization of the supply chain and the items regarding user interaction. The first challenge is the complexity of the systems in the manufacturing industries, which often operate in uncertainty and constant changing environments as per the variation in the customer domain, or changes in product design, or actually processing technologies. This uncertainty adds up to the fact that there may be a restriction, for example, in the flow of technology or communications that can derive from legislations and differences across borders. With such uncertainties, the complexity of designing systems increases, which makes the problem for digital twins, because then it will lead to higher complexity and higher costs. The classical sequential system engineering works with physical objects in the manufacturing environment. The process requires converting the design into a prototype, which is not only expensive for the minimal corrections that it allows to perform, but also time-consuming if the validation goes wrong and the designers need to go back to the design phase. In the case of integrating digital twins, the digital twin has the ability to change this traditional approach with a model and simulation that is performed digitally. Working with digital models in the creation phase is cheaper, faster, as it shows that the downstream functions can influence the design. So instead of having to deploy and create physical prototypes in order to assess and evaluate the product, companies can now do the entire process online and digitally. So they can create engineer models, perform transition to a simulation environment that can replicate the physical environment, and then perform validations and go on through this cycle. Once there is a good release, then there is indeed the integration into the physical space, which then may require go back or not, or simply to monitor the new systems. In this slide, I'm presenting one of the research projects we have been working in the past years. In this case, we have designed, for example, what you see in the right side is a digital twin composed of two parts. One part is users are able to analyze the current state of all elements in the shop floor, and in the other component, which is a web application, different stakeholders can actually integrate and test their own production algorithms that then can be submitted to the company for real production. So this allows third parties to test and deploy their data into a simulation digital twin that provides the same behavior as the manufacturing plant and test their own algorithms. But on the other side, they can also track the manufacturing process of their processes. The advantage here is that this exchange of information allows for a much better coordination between these companies and decrease the times that are required from the design to the manufacturing. So small industries usually have their own system for communicating, accessing data online, or storing data. Industries like aerospace and automotive and manufacturing have a large number of standards that need to be followed in order to ensure that third-party communications or product or human safety are adequate and enforce the proper security. In this image, we can see the complexity of the manufacturing chain. So we have the company that is manufacturing needs to interact and communicate to a large number of other third-party stakeholders like part supplier, component supplier, material processors or material producers, but also with logistics that can interact directly with the client or not. This cycle ends up with the dismantle of the devices that are produced, or even with follow-ups regarding maintenance and repair of the services. So in order to receive maximum benefits of using a digital twin, we need to enforce a way that standards can provide and enable the communication between all these stakeholders. This communication then has its own benefits that, for example, the manufacturing industry can optimize the production based on a simulation of the expected times for suppliers to deliver parts and the amount of parts that are delivered, as well as demand from customers and logistics. Another challenge with the digital twin is the scalability. This is probably one of the most critical and involves many sub-challenges. Well, scalability can be defined in terms of architecture, data load, ability to change the level of parameters, the supply chain complexity, or computational ability and architecture. Therefore, the scope of the digital twin may vary from a simple product to high complex processes or manufacturing systems that offer desired accuracy based on smart data analytics. So, an example is the example of certain types of data. For example, complex data CAD systems may have to be downward scalable in order for huge amounts of data that require large amounts of memory and processing be able to be useful for different stakeholders and users involved. So a very complex model in this image could be, well, shared is not a very complex model, but this is an image that transmits the idea. We have that designers don't require all the information that is in that model, the mechanical information. They just care about the design of the object. But then we have engineers that on top of that information have to use simulation algorithms, and they have a different type of data structures in order for them to test and evaluate the product. At the end, we have that this product can also be represented for stakeholders. It may not have all the engineering information, but provides a different types of visualization, like the aspect of the material and so on. So this means that one single product may have to be readjusted across the chain to meet the needs of each of the stakeholders and still maintain its consistency. This is what is important here in the information sharing. So data sharing can be segmented into two groups. The first one is internal data sharing, and the second, external data sharing. The internal data sharing refers to the pooling of data from different departments within the company, and the external data sharing takes place among the stakeholders across the supply chain. In the modern manufacturing, information sharing across the value brings tangible benefits, but the people involved in the process sometimes pursue different goals, and this kind of mentality makes information sharing very difficult. So for an integration system like a digital twin to work, we need both kinds of data. However, the lack of information sharing forces the creation of silos, as we see here in the image. And these silos tend to arise in organizations because that different departments share different goals or priorities or even responsibilities. There are a number of information formats as well that, depending on the department, may be useful or not. So there is also need for translating these formats into formats that are useful or can be used by the party taking the data in that specific node. So another important aspect is, and this is probably the aspect that's becoming every day more important, is that the manufacturing and the service industries are upgrading their portfolio to increase the value of their services. So by integrating products and services all together. This means that they are adding services to products that otherwise would be offered in the downstream position in the value chain system. All these services are based so all these services can not only provide the service to the client, but also be used to collect data about the product that is being served. And with this data and the use of the digital twins, companies can actually continuously learn about their use and improve future releases based on historical data of the asset. So this is a project that we follow more or less the challenges that I just described. What we have here is a machine tool. It's a machine that is designed to create pieces. And what the company wanted to create was a digital twin that would start at design phase. So from CAD models, all this data would be part of the digital twin, and later on it will be received from a different user that would create all the technical materials for maintenance and support of the end users, but it will also connect to the physical prototype. So data from the real model, physical asset, would be collected and analyzed within the system. With this digital twin, there was the deployment of two different applications. One was the augmented reality application. Is the one we see there is a augmented reality application where there is a digital version of the model superposed over the physical machine. So users can see data that is being collected from the machine directly using a tablet and perform maintenance operations with that same tablet. With the same system, it's also possible to use the virtual reality experience. Here, the service is towards a different type of users, towards training of new operators, and the same system allows to create immersive experiences where users can train the use of the application or even the maintenance operations. In this case, the machine, the behaviors in virtual reality are automatically created from the topology of the mechanical pieces, and there is little effort and there is no programming involving from passing from the CAD model to the virtual reality or even the augmented reality. So there are two challenges associated with technology. The first is time and cost. This means that complex assets that often comprise multiple twins can be organized into larger twins. But due to such complexity, we need to separate development, integration, and deployment, which is required now for each layer and adds some extra complexity. So with this complexity, we have a number of components that increase, and therefore the IT costs associated with this will increase as well. This raises the cost for deploying an effective digital twin. So it's very important to understand when a company wants to design or create a digital twin, which is the business model or the purpose that we want to give to that digital twin. Otherwise, we may fall into this loop that just makes costs increase, and at the end, you may not get the return from the investment. Then the other problem is inherent to the cyber-physical systems. The deployment, the development, and implementation of digital twins depends on systems and services that are operated by third-party stakeholders. This means that difficult sometimes to access the data, or the data is not available, or the strategies that are used to access the data are not the best for this type of interaction and systems. So here is one of the most critical probably challenges for the companies to implement, and overcoming this issue is very difficult unless there is a common effort towards trying to provide more homogeneous, and I talked before, standard ways of communicating between machines and also other assets such as humans. So the variety of data is another of the challenges of digital twin. Well, this challenge is inherent to pretty much all visualization platforms and applications, but here it's also severe. So the variety of data generated across the life cycle of a product is massive. Well, starting with the product development, we have that design data can be in 2D, 3D, and be represented using finite element analysis or integrate simulation data. So this means that within the same department, you can have multiple formats, and across departments, you also have multiple formats. So this makes it very difficult for the communication and exchanging data between different parties. So the issue here is that data has to be prepared for different purposes, which requires time and costs. Okay, now I'm going to start talking a bit about what I would like to talk in this presentation. So the consistency of data and information sharing are fundamental for the validity of the digital twin. It means that it requires greater coordination and operating practices, as well as standard and data architectures that also must be flexible to adapt to the future requirements. So the digitalization of the supply chain is fundamental. It provides an understanding of the entire production chain and a good overview of what the system can do and where it can be optimized. Within the digitalization, we start to face many issues. One is how we acquire data. Data can be from engineered drawings. In this case, we may get very large models that can be in different types of representation, like parametric, and you may also have two 3D scans of the shop floor in order to digitalize some of the elements that you can find there. But this also requires filter some noise in the scans, alignment, as was previously described in the talk, as well as good processing of point clouds. So this is just the aspect that talks about acquiring data, but then we must also keep in mind that this data has to be used, and in most solutions it has to be interactive. So digital twins are designed for humans, so humans need to interact with technology. This means that they must be adapted, which may require simplification or data processing, as well as other kinds of enhancements. So we may need to actually add additional information to these models and scans in order to enrich them and make them easily understandable by different users of the system. Additionally, it's also important that not only we capture the physical geometrical aspect, but we can also describe it in terms of behaviors. This includes, for example, kinematics, as well as materials, and so on. So before I show this machine, this is a punching machine. So it's a machine that can move metal plates and punch them. Then the machine itself can also select different tools for punching. And then it involves a process that creates from these metal plates different objects that are then used as a part in other manufacturing objects. In this case, in this digital twin, it's possible for the users to load the 3D models that they want to manufacture and define which are the actions and optimizations that the machine should execute in order to manufacture them. And together with this digital twin, we have two applications that are controlled. One is the application, it's called G-code, that provides interaction with the elements, and the other one allows to control the punching tool that is active. So with this digital twin, not only the company can control and monitor in order to actually predict any maintenance and so on, but can also understand the removal of materials, how much material is discarded, what is the quality of the material in terms of eating, as well as how all this process can be optimized. And this they can get from simulation algorithms that are integrated and have access to all the information about this particular use case. Another digital twin, another example that talks a bit as well about the digitalization of the supply chain. In this case, it's just a virtualization of warehouse inventory. So here we can see a real representation of the physical warehouse. And this digital twin not only contains the virtual representation, but can also obtain inventory in real time from a different system. So it must also connect to other services in order to keep itself updated. In this case, we don't have, for example, a machine that fits the digital twin with data, but we have a service. This allows the users of the system in order to plan and understand the workflows in the warehouse inventory. Well, data integration is the next step and is one of the primary drivers behind the concept of digital twins. It enables analysis of both structured and unstructured data for both internal and external sources to give a deeper insight into the physical machine or process. Therefore, all data streams need to be consolidated to deliver a single source of truth. This means that the data collected from sensors must be processed, and the input and actions received from users must also be integrated into the system to provide the proper feedback. In this case of digital twin, we have a digital process that is associated with a manufacturing device, which, similar to the previous one, manufactures objects from metal plates, in this case, metal sheets. In this case, the tool that is used for the manufacturing is a laser. And when you try to manufacture some specific parts, you need to design the machine to follow specific cutting paths, which, depending on the material, there is a heat transfer between the laser and the metal sheet. This means that you need in order to manufacture a product, you need to have this physical machine well connected to a digital replica where you can, before producing, analyze and simulate what could be the unforeseen anomalies that can be generated from cutting different parts of the object at close distances, which would, through heat, damage or deform the material. So in this case, you are able to understand a priori the challenges and optimize the manufacturing process by observing and visualizing the side effects of cutting using a determined path, and then send it to the real machine and observe the manufacturing process and the data that is being collected from the real machine. One case more of a digital twin that was or could be seen as a digital twin in this case is a firefighter training program. We, in this case, created an application where data from the public data sets about the city, such as the weather forecast, which includes wind direction and speed, could be used, as well as information about the digital terrain model and the building as itself. In this case, we just use data from OpenStreetMaps, but if you think of this as having a beam model for each model, then the simulation could be even more realistic and really take into account the properties of specific buildings during the simulation. So in this case, fireflies could experiment in a real simulated environment how different scenarios could take place and how they could fight back these fires. In this case, they would be training in using data from the real place. In this case, it's San Sebastian. And from the training, not only they would learn about the algorithms and ways of fighting the fight, but also about the environment itself. So the location of buildings, properties of the terrain, and so on. So another key challenge in the creation of digital twins is human interaction. Human interaction is one of the key aspects in the development and implementation of digital twins. But it's also a problem because human actions and interactions with machines in the production environments are prone to accidents. And therefore, we must develop safety mechanisms to solve this issue. The problem is that unlike technical systems, humans cannot be easily monitored. There are techniques that can use cameras to track workers and so on, but this kind of information is still very limited. So there are two outcomes of this limitation. One is that these new smart systems have to talk to each other and exchange information without leaving space for human involvement in the decision making, because if they wait for human involvement, then the entire process gets blocked by the fact that it's not advancing. Human decisions are not taking place at the same speed. So another direction here is that the decision-making process has to wait for the human inputs. And these human inputs, in the case of digital twin, can be gathered automatically. So throughout the human digital twin, we can immediately gather user feedback that can be generated or use it for computational decisions by the production system. This may not be enough, as the data is limited nowadays to a definition of skills. So a user is associated with a list of skills, experience, and preferences. So there is still some research that is needed here to understand and collect more influences that affect the user decision. For example, influences like the mood or other aspects or disabilities of the user that may affect its interaction with the environment. So this is another example of a digital twin. In this case, its focus is the disabled people. And what we have here is a digital twin for an electric cabinet. So electric cabinet is a device that in this case has to be assembled manually by a worker. And this digital system allows the supervisors as well as the workers to understand which is the current state of the device that is being manufactured and interact with the system in order to obtain information. In this case, for example, the worker can naturally interact with the system and ask information about which is the position or which cable and how the cable should be wired to the device. The system as well can understand the user and try to help him with different visualization modalities. Could be visual, but some of the users have limited vision, so audio was also used in that case. Some users don't know how to read, so in that case they would interact verbally with the system using a natural language, or some users were not able to read diagrams, schematics, so they would have access to interactive videos where they could learn and understand how the operation could be performed. So all this process is a seamless interaction between a worker, a digital twin that collects information from the environment and the production, and interacts again back with the user to provide the information that he needs to accomplish the manufacturing. So this leads us to the last challenge, which is related to the security. So how can the digital twins and its platform be secured? So there is a huge intellectual capital being invested and available in these digital twins. So any data security threat can damage information, the reputation of the company, the finances, or even destroy or affect the physical assets. This means that illegally accessing digital twin could enable the attackers to control the plant and perform changes that could be harmful to the production. So now to conclude the presentation, I will talk a bit about the next steps. What we are seeing now is, let's say, the exodus. We started with robots that would stay at the shop floors, and eventually they start becoming more dynamic. They start to move. They start to perform other operations that include, for example, logistics and so on. So we are moving towards a global world of connected smart systems. This means that connected factories, connected buildings that can store, for example, manufactured products, connected cities where the logistics happen, connected grids, vehicles that are transporting materials to the factory or from the factory, as well as state of the roads in order to optimize the transport. So there are talked about digital twins. I gave many examples. All these examples were located at different factories. So what if, for example, we talk about a very large chain of production that not only covers a closed environment, but starts to deal with a lot of mobility or works with a lot of assets, can be digital twins themselves that are distributed, and how can we analyze that information and all those spatial trends that are also a temporal dimension. So how could we bring together the information and insights that concern not only a digital twin, but also the entire environment that can be distributed all over the globe? So this is not a new concept. If we look at this web page, we can see what we could describe. For example, the airplanes could be the digital twin that would provide all the information about the airplane. In this case, they provide just the flighting path, but with this platform, not only we could access the state and visualize all the digital twins together, but we can optimize at the macro scale how the process could be further refined for better results. And my last thoughts are that, well, now we are in the face of a pandemic problem. We see that many demands in the manufacturing industry is decreasing. This, in one way, is because of logistics. Now, workers that work in logistics face the challenge of having to go outside and deliver the products, which puts their health in risk. But at the same time, we are also seeing that many of these processes are starting to get automated. So probably we are not there at drones transporting materials and delivering directly at the client or customers, but soon we can be there. And at this stage, we will be talking about the global scale. So different parts suppliers are located in different parts, which can be countries or at local scale like cities, but still not closely by. And then we have the industry that is receiving all those parts and assembling them and adding added value to the product that then can be delivered again to the client and vice versa. So we can see there are a lot of challenges here that cover not only the manufacturing, but the logistics that are involved. And it's very important to understand this logistics because you can optimize the manufacturing process based on the demand as well as on the supply of materials that you get from your suppliers. So how can we better understand and optimize processes in the case of that we are now moving towards a global scale integration and automation? This is where I start to see that this geo platform starts to play a very important and key role that can give companies a bigger picture of the entire business. Well, this is for now all. I will be very glad if you have any comments or would like to discuss these concepts. We can also see that there is a lot on the geospatial domain. So a lot of standards that have been developed concerning the representation of buildings, concerning representation of large spaces, and we need to capitalize on these lessons that we learned from that and bring them together into the industry domain so this problem can be solved in a more efficient way.
Bruno, thank you very much for your presentation. I really enjoyed a lot. Probably also for the familiarity I have with your research and the time we have spent together in reasoning about this, reflecting about this aspect. Actually, there is one question which you probably have seen. I don't know, but it has been forwarded by Bill, one of our one of the organizers of this workshop, and actually is asking about your opinion regarding the ISO standard for digital twin, the ISO 23247. I don't know if you, I would like, or would be interested if you can comment on this request, this question from Bill.
Yeah, so as I mentioned before, standardization is really a problem because it starts with the fact that most companies have their own proprietary formats, and the tools that they use do not allow them actually to move to open formats, ISOs, for example. And this raises the challenge for them. You know, they are locked down to a solution, and now they cannot move out of this solution. But as you said, there are a number of standards that already cover most of the needs that these companies could use. So we have, for example, formats like STEP that could describe the entire product from a mechanical perspective with different profiles. And there are also tools that allow the transformation of these formats into other formats that can be used on the web as well as on geospatial applications. For example, the conversion to X3D would allow easily the integration as a web visualization platform, and then other formats can also be used for the visualization in other systems.
Thank you, Bruno. And I mean, we are really getting close to the end of this workshop, which actually took a lot of effort to be organized and also implemented. I'm extremely happy about the results we achieved all together in also facing the complexity of still an unexplored domain. Only certain aspects like the one that Rafael as explored very well in our are, let me say, relevant for most of the scientific community that is composing the one of related to augmented reality. There is still, in my opinion, a lot of benefit. I mean, I would say that standard are by definition part of the solution of the challenges that we are facing. And I really appreciated, Bruno, your last slide, especially when you were highlighting the importance of Industry 4.0 is not limited at the shop floor, and the interaction with the industrial asset is not bounded into the constraint of an indoor environment. I truly believe that if there is a different vision similar to the one that has driven the CTGML standard that should support this kind of research activity. I would be glad also to get the opinion of Bill, Joshua, and Johannes and Rafael in this regard, now that we still have 6 minutes, if I understood the timing of the workshop. So please, go ahead, guys. Especially if you're still here.
Yes, so I'm here. This is Bill. So yeah, I can respond to the digital twin perspectives. That surely digital twin has a lot of benefits and advantages once it's implemented. It is very expensive to properly build one, and of course, because of the expense or the cost of doing such, getting to the point where you can actually claim that that's why I think the standard, I don't even remember that because I don't work on it explicitly, 23247 ISO, it's not necessarily providing any representation or format for translation or transition. It's more about kind of setting the tone for the terminology and definitions of what is a digital twin. As Bruno, I agree with Bruno that a lot of things have already been done. For instance, let's take the flight path example that he showed. You know, there's sensors, you know, all over the world. It's been that way for quite some time. And to build a web app to visualize the outputs of those sensors has surely been realized. The question becomes, what is a digital twin? What makes this a new idea? And at least that's what the standard is starting to address. And it's very interesting because I haven't been sitting in the meetings, you know, full disclosure, but my colleagues have. And I will just mention that it's not an easy thing to define because, as Bruno rightly points out, there's many different perspectives and many different kind of just simple definitions out there. And I know that it was contentious to even pass. I think they're at the draft stage. So I do think it's important to also maybe we can talk about this in the future together, like where AR fits into this picture and how important it is to the digital twin journey. Yeah, to me, it's an unanswered question.
I think it's important to consider still and maybe always the digital twin is a really useful ideal and design principle. But as important as it is to figure out what a digital twin is to figure out what a digital twin is not. Because there's as you said, incorporating a sensor into an understanding of how the non-digital twin is behaving is very valuable, but not understanding what the sensor is not sensing is equally dangerous. So I think there's a lot to do in terms of defining exactly the scope of what is termed a digital twin. We tend in the larger scale of urban digital twins, which OGC is involved in quite a bit right now, to look at the digital twin twinning some aspect of the, for example, of the urban system, that is in terms of an energy digital twin or a water digital twin or a mobility digital twin, and using at least the terminology to define the scope of the, the emulation. But that, I think is incredibly important and part of the sensor web GeoIoT approach, is to be able to let people know what they should not expect a digital twin to be telling them.
Joshua, would be very glad to collect your opinion with regard to one of the item I introduced in my presentation. And my question for you is, if you think if there is a need for a data model similar to the one of CTGML, but for the industrial context.
Yeah, I've had discussions about, is CityGML appropriate for that? And, at some general, but two problems. One is it doesn't necessarily cover the relationships that, an industrial infrastructure would like to have modeled. And what we haven't really done is to investigate whether an application-specific extension to CityGML would fill that gap. So that would be very interesting. The other thing is that CityGML is not yet very good at moving parts. It's pretty good at structures, but the parts that move, I'm not sure that an extension will succeed in representing the relative relationships that would imply. So I think there is application of CityGML to be tested, but I think there are limitations.
Yeah, I second your opinion. I think that CityGML has demonstrated to be a very important tool exploiting the potentiality of graphical information in an urban context, but I truly believe that there is a need to a similar effort for industrial area and asset as well. Also, I don't think I agree that the extension schema or model provided by CityGML would be enough, would be sufficient to that's really the point.
Yeah, I believe there are many good standards available, and one of them is the CityGML. But as I mentioned before, these different departments have different needs. So which is the need of using CityGML? Perhaps to represent the entities that are part of a city. But then when you move to low level in a factory is a building in the city, so it could also be part of this specific format, and all the machines inside the factory could also be represented. So what is probably missing is a way of connecting that specific standard to other standards that are widely used as well in manufacturing, like for example, for representing the CAD models that have the mechanical behaviors and so on, rather than having this standard that describes the entire universe, which would require, of course, the creation of applications that would translate the formats that companies actually use into that format, and then merge a huge number of data sources as well. So perhaps one of the easiest ways to take it was actually to promote the synergy between different standards into a way that they can actually co-interact and function all and live together.
Actually, that's exactly what when we look at ontologies and the research in ontologies is telling us. So basically, like 20 years ago, we were trying to come up with a single ontology that describes the whole world, and they totally went away from this idea because they said, well, it's way easier to have smaller domain ontologies to help us to understand and model a single domain, then use like an upper ontology to bridge the gap between those single domain ontologies. So basically what we might need, or what we might look at, is how to combine different, let's say, standards, data models, whatever, in a clever way in order to come up to preserve semantics, in order to bridge the gaps between the different models, and to, let's say, also have the ability to connect different, let's say, viewpoints, different scales that are there, and all that stuff. So because not every model or every standard fits every single purpose that's around here. Meaning like you said, Bruno, sometimes you need a CAD model is for like the mechanical functioning of a process. Sometimes it's you need just the manufacturing device that's necessary to visualize it, to have geographic environment, and that different, let's say, scale that you look at needs to be somehow represented, and one single model doesn't fit everything, or doesn't fit every purpose, right?
Yeah,
Yeah,
I completely agree with you.
Yeah, Johannes, there's a very interesting effort called the Industrial Ontology Foundry. That's IOF. You should be able to search at ioffoundry.org, I believe. And all the same players, have been mentioned here, know about it, at least some are part of their organization. And the approach they're taking is, rather than describing something like schema.org, right? Schema.org kind of presents everything, and it always fails. Well, I shouldn't say always, I'm sorry. But for domain-specific problems, it doesn't seem to address issues. Rather, what they're doing is basically governing the contribution of individual ontologies to this foundry or database, so that even though that they expect to have coverage in particular areas, they can at least have some governance in that these ontologies that are there can work together. So they base them off of a I don't know if you meant upper ontology like the BFO, the basic formal ontology. But yeah, basically everything has to adhere to something like the BFO, or else it's not, or it's rejected from the from entry into the foundry. I think that's a decent approach, but we'll see if it works. So excuse me for my daughter in the background. She's excited about the conference. Yeah.
You know that there is no need to excuse for these things. Just a super fantastic sound that is complementing this discussion. I think that the data model of an industrial asset or in the factory, in principle, is not the biggest barrier we can have in this endeavor. CityGML was still is a great way how to model an urban environment, and was capable to exploit this potentiality, thanks also the effort to store the data in an efficient way to be processed, in the effort that, for instance, people in Berlin has done in the 3D city database. So this is probably also it's something that you build, you said at the end of your presentation. So what kind of then geometrical kernel we use to, you mentioned Open Cascade, for instance, we can mention also ACES for spatial. We are going to eventually consider to store the geometrical information and also enhance them with the appropriate metadata. So to describe this ecosystem as I define it. I think this is together probably with the point of, and this has been basically with the IndoorGML in using not an internal representation, how to store the data, for instance. Very completely different approach. I think we are getting, we are probably now even out of the time we had at our disposal. And I believe that in Europe it's quite late in the evening. So I was wondering if there is any other question from the audience, probably by means of the other platform, which actually I don't have any evidence of this. Otherwise, probably we can get to the end of this workshop and enjoy, yes, for the efforts that we probably have to replicate this workshop also in 1 year from now and see what kind of progress we are able to collect, also inviting other colleagues in this kind of discussion. I would like to thank you, each of you, Bruno, Bill, Johannes, Rafael, Joshua. Yeah, that's great. It has been a kind of fact, I have to say, but I'm super happy about the results. Hopefully 1 year from now, we can meet all together in a real way. And I'm sure that we will keep the discussion going on via Zoom, WebEx, or emails. So thank you very much for everything. And if you would like to provide your last comment, please go ahead. I don't want to have the last word in this call.
Well, I'll take the opportunity just to thank you, Raphael. We couldn't have done this without you. You really put in all the time to get us to herd all the cats. So thank you very much.
Yeah, no, I mean, I am the one that has to thank you. Because of the interest topic you brought in this discussion. I always say this, my colleague always motivate my research vision. And I think that this group of people can really, probably we can think about to do also something together, coupling the two sides of the Atlantic, Europe and USA, also inviting some friends from other parts of the world. I would like to thank you again, each of you, and I wish you a great rest of the day or a good night, wherever you are. And also, I would like to thank you, all those people that are working in a domestic environment. I'm sure that we are to appreciate the environment you have at home that is supporting us in doing this thing. So thank you, everybody. Thank you, our audience, and I'm looking forward to see you working with you once again in 1 year from now. Thank you.
Thank you, everyone. Thank you for listening and for your opinions.
Great. Goodbye.
Thank you. And good night. See ya.
Good night.